Hello there, and welcome to Science for Sleep, a place where curiosity slows down, questions are allowed to linger, and science takes its time. Wherever you are right now, whether the lights are dim or already off, whether the day has just ended or the night is still unfolding, you're very welcome here. This is a space designed for gentle thinking, for ideas that don't rush you, and for explanations that feel steady rather than demanding. Tonight, we're going to talk about something that sounds simple at first but becomes stranger the longer you sit with it. We're going to talk about emptiness, not the emotional kind, not the feeling you get when you open the fridge and forget why you're there, but the literal emptiness of the universe itself, the vast stretches of space where almost nothing exists, the enormous gaps between stars, between galaxies, between anything that could reasonably be called something. There's a common picture many of us carry around without really examining it. When we think of the universe, we imagine it as busy, crowded, filled with stars in every direction, planets everywhere, maybe life popping up constantly like weeds in a sidewalk crack. Science fiction hasn't helped much with this image. Spaceships dart from system to system, alien civilizations sit just around the corner, and the cosmos feels like a bustling city if you zoom out far enough. But the real universe is nothing like that. In reality, it is astonishingly, almost offensively empty, and there is a reason for that. A reason that isn't just technical or mathematical, but deeply unsettling once you fully understand it. A reason that raises uncomfortable questions about life, survival, and how fragile complex things really are. We'll get there slowly. No rush at all. Before we drift further, let me ask you something simple. Where are you listening from right now? Are you lying down, sitting, pacing quietly, or letting this play in the background while you settle in? And what time is it for you at this moment? Not the official time on a clock somewhere far away, but your time, the part of the day or night where your thoughts begin to soften and stretch out a little. If you find this calming or interesting, or just a good companion while your mind winds down, a like or a subscription quietly helps this space reach other people who might need the same kind of pause. No pressure at all. Just something to keep in mind as we continue. Now, let's begin by looking upward. Not in a dramatic way. Just the simple act of imagining the sky above you. Even in the darkest places on Earth, where city lights don't interfere, the night sky shows only a tiny fraction of what's actually out there. A few thousand stars, a hazy band of the Milky Way, maybe a planet or two depending on the season. It feels expansive, sure, but still intimate enough to wrap your head around. You can trace constellations, recognize patterns, give things names. What you're seeing, though, is a kind of illusion. Not a falsehood, but a misleading sample size. Almost everything visible to the naked eye belongs to a very small neighborhood, a thin slice of a much larger structure. Beyond that familiar glow is an emptiness so extreme that it's hard to describe without numbers, and numbers rarely do it justice. Between you and the nearest star system beyond our own lies a gap of over 4 light years. That's not 4 years of driving or flying or even drifting. That's 4 years of light, moving at the fastest speed anything can travel, crossing nothing but vacuum. No clouds, no debris, no friendly roadside stops. Just distance, and that distance is considered close by cosmic standards. Once you move beyond stars, the emptiness becomes even more severe. Galaxies themselves, which contain hundreds of billions of stars, are separated by voids that stretch millions of light years across. These voids are not filled with hidden cities or undiscovered civilizations waiting just out of sight. They are regions where matter is so sparse that calling it empty still feels like an understatement. On average, the density of matter in the universe is only a few atoms per cubic meter. Not per cubic centimeter, per cubic meter. A volume large enough to hold a person contains, on average, less matter than the air inside your lungs at any given moment. And much of the universe is even emptier than that average. This isn't a coincidence. It isn't an accident. And it isn't just a boring footnote in astrophysics textbooks. The emptiness is a result of how the universe behaves at the largest scales, how it evolved from its earliest moments, and how hostile it is to complexity. It reflects a long history of things being pulled apart faster than they can come together. A history where gravity struggles to build, while expansion relentlessly tears space wider. To understand why the universe ended up this way, it helps to briefly rewind to its beginning. Not with drama or fireworks, but with something quieter and more important: conditions. The early universe was not empty, quite the opposite. Shortly after the Big Bang, matter and energy were packed together in an incredibly hot, dense state. Everything that would later become stars, galaxies, planets, and eventually people existed in a form that was almost uniformly spread out. There were no vast voids then, no lonely regions, no empty expanses stretching on forever. But that state didn't last. As the universe expanded, it cooled. As it cooled, matter began to clump together under gravity. Tiny differences in density, barely noticeable at first, became seeds for structure. Regions that were slightly denser than average began pulling in more matter, growing over time. Regions that were slightly less dense lost matter to their neighbours, and became emptier still. This process didn't create a smooth distribution of stuff, it created a cosmic web, filaments of galaxies and clusters strung along invisible scaffolding, with enormous voids in between. Think less like evenly spread sand, and more like a sponge, dense where it's solid, hollow where it isn't. The key detail here is that once emptiness begins to form, it tends to reinforce itself. Matter flows out of low-density regions toward higher-density ones. Gravity deepens wells where matter already exists, and leaves other areas increasingly barren. Over billions of years, this process exaggerates the contrast. The crowded parts get more crowded. The empty parts become astonishingly empty. At the same time, the universe itself is expanding, not just moving outward into something else, but space itself stretching. Every large-scale distance increases over time. Galaxies are not racing through space away from each other, so much as being carried apart by the expansion of space between them. This expansion doesn't slow down the formation of emptiness, it accelerates it. As space stretches, matter thins out. Even regions that once held gas and dust find those materials spread more and more sparsely. Over very long timescales, stars burn out, galaxies exhaust their fuel, and the universe trends toward a state that is darker, colder, and emptier than anything we currently experience. All of this might sound bleak, but so far it's just physics, impersonal, mechanical, nothing terrifying yet, just a universe following its rules. The unsettling part emerges when we ask a different question. Not how empty the universe is, but why life exists at all within it, and why it seems to be confined to such tiny, isolated pockets. From everything we know about biology, chemistry, and planetary science, life is not easy to start. It requires a very specific set of conditions: stable energy sources, complex chemistry, long periods without catastrophic disruption, a delicate balance between change and stability, too much chaos, and nothing complex survives, too little, and nothing interesting happens. The universe does not naturally favour these conditions. Most of space is hostile to life in ways that are difficult to exaggerate. Temperatures near absolute zero, intense radiation, vacuum that tears molecules apart, timescales that dwarf anything biological systems can tolerate. Even within galaxies, most locations are unsuitable. Too close to the centre, radiation and gravitational chaos dominate. Too far out, heavy elements become scarce. Habitable environments are rare not because the universe is lazy, but because it is aggressive in its simplicity. It expands, it cools, it smooths things out. Complexity is something that must fight against this trend, locally and temporarily. This leads us to a quiet but profound realization. The emptiness of the universe may not just be a backdrop, it may be a filter, not a designed one, not an intentional barrier, just a natural consequence of how reality works. Structures form, but they are isolated. Life emerges, but it is fragile. Intelligence develops, but it is vulnerable to both internal and external threats. When we look out into the vast silence between galaxies, we are not just seeing absence, we may be seeing the result of countless failures, places where complexity never arose, or arose briefly and vanished, regions where the conditions were almost right, but not quite, times when the universe moved on before anything lasting could take hold. This idea doesn't require speculation about aliens or advanced civilizations. It doesn't depend on science fiction scenarios. It arises naturally from the same processes that shaped stars and galaxies: expansion, gravity, entropy, and time. Entropy in particular plays a quiet but relentless role. The universe tends toward disorder, toward spreading energy out evenly. Life is an exception, a temporary reversal, a local pocket where energy flows in structured ways, building and maintaining complexity for a while. But entropy always wins in the end. The emptiness we observe today is not static. It is growing. Voids are expanding. Galaxies are drifting farther apart. In the far future, many regions of the universe will be so isolated that observers within them will see only their local galaxy, surrounded by darkness. The larger universe will effectively disappear from view. From that perspective, the universe doesn't just look empty, it becomes functionally empty. As you sit with this idea, it's worth noticing something subtle. Despite all of this, here you are, thinking, listening, existing in a universe that overwhelmingly favours nothingness. Against staggering odds, complex matter assembled into a planet, chemistry into biology, biology into consciousness. This doesn't make the emptiness comforting, but it does make it meaningful. The terrifying reason the universe is so empty is not that something removed everything else. It's that emptiness is the default. Complexity is the anomaly. And anomalies, by their nature, are rare, isolated, and temporary. We'll explore how this connects to questions about other civilizations, cosmic timing, and the possibility that survival itself is far more difficult than we like to assume. But there's no need to rush toward those ideas yet. For now, just let the scale settle in, the vast distances, the quiet, the realization that the universe is not crowded with neighbours but defined by separation, defined by the immense spaces where nothing happens for billions of years at a time. At some point, almost everyone has the same small experience. You step outside at night, maybe without planning to, and you look up. Not to search for anything in particular, just out of habit, or curiosity, or because the sky happens to be clear. For a moment, everything else fades into the background. Conversations pause, thoughts slow, your attention lifts away from the ground and settles on what's above you. From Earth, the sky feels generous, dotted with light, alive. Even a modest view shows stars scattered across the darkness, some brighter, some faint, some twinkling slightly as the atmosphere bends their light. It gives the impression of abundance, as if space is filled with objects, each one close enough to matter, close enough to keep us company. That impression doesn't survive closer inspection. What you're actually seeing is an extreme form of selection bias. Only the brightest, nearest stars make it through the filters of distance, dust, and your own eyes. Everything else, which is most of what exists, is too far away, too faint, or too spread out to register at all. The silence between those visible points is not decorative. It is the dominant feature. Once you start paying attention to that silence, it becomes hard to ignore. Between Earth and the Moon, which feels close in everyday terms, there is enough empty space to fit every planet in the solar system with room to spare. Between Earth and the Sun, a distance we call an astronomical unit, there is almost nothing at all, a few stray particles, the occasional solar wind proton, vast volumes where, if you were to pass through, nothing would touch you. Even within our own solar system, space is not busy. The planets occupy tiny regions compared to the distances separating them. The asteroid belt, often imagined as a crowded obstacle course, is so sparse that spacecraft routinely pass through it without any risk of collision. On average, asteroids there are hundreds of thousands of kilometers apart. That's still the dense part. When you move beyond the Sun's influence, beyond the heliosphere, the density drops further. The nearest star system, Alpha Centauri, is so far away that if the Sun were the size of a grapefruit, Alpha Centauri would be another grapefruit several thousand kilometers away, with nothing but emptiness in between. This emptiness is not just spatial, it is energetic. There is very little happening in most of the universe. No reactions, no processes, no change at scales that matter to living systems. Just slow expansion and gradual cooling. It's worth pausing on that word, silence. In everyday life, silence is rare. Even when things seem quiet, there's background noise, air moving, electrical hums, distant traffic. Biological systems are noisy by nature. Cells communicate, hearts beat, brains fire. Life is full of signals. The universe, by contrast, is mostly mute. There are places where things happen, of course. Stars fuse hydrogen, supernovae explode, black holes consume matter and emit radiation. But these events are localized, tiny sparks in an ocean of stillness, and they are separated by distances so large that their influence often fades long before it reaches another region of activity. This separation is not accidental. It is a consequence of how matter behaves when space itself is expanding. As the universe grows larger, matter does not automatically fill the new space. Gravity works locally, pulling matter together where it already exists, but it does not act fast enough or far enough to keep everything evenly distributed. Once regions become underdense, they tend to stay that way. Matter drains away toward denser regions, leaving behind increasingly empty volumes. Over time, this process exaggerates contrasts. The universe develops structure, but that structure is filamentary. Long strands of galaxies connected like a loose web, surrounding enormous voids where almost nothing remains. These voids are not small gaps. Some are hundreds of millions of light years across. Inside them, galaxy formation is rare. Star formation is minimal. Chemical complexity struggles to gain a foothold. If you were located inside one of these cosmic voids, the night sky would look profoundly different. There might be only a handful of galaxies visible, faint and distant. The sense of isolation would be extreme. The idea that the universe is filled with activity would never even occur to you. From that perspective, emptiness would not feel like a mystery. It would feel like the norm. This brings us to a subtle but important shift in thinking. When we ask why the universe is empty, we often treat emptiness as something that needs explaining, as if fullness is the default and emptiness is the deviation. But physics suggests the opposite. Emptiness is what naturally happens when energy spreads out and matter thins over vast scales. Structure is the exception. To create a star, you need gravity to overcome expansion locally. You need gas to cool, collapse, fragment, and ignite. To create planets, you need heavy elements forged in earlier stars. To create life, you need chemistry complex enough to self-organize and sustain itself over time. Each step requires specific conditions and long periods of relative stability. Most regions never meet those conditions. This is where the silence becomes unsettling rather than just interesting. When we look up and notice the gaps between stars, we're not just seeing physical distance, we're seeing barriers. Not walls or force fields, but practical limits. Limits on communication, limits on travel, limits on influence. Even at the speed of light, messages take years, decades, centuries or longer to cross the distances between stellar systems. For anything slower, like spacecraft or biological organisms, the gaps are effectively impassable with current or foreseeable technology. The energy costs are enormous, the timescales are prohibitive. This means that whatever happens in one pocket of the universe is largely irrelevant to what happens in another. Civilizations, if they exist, are isolated. Life, if it arises, does so alone. Successes and failures do not propagate easily. There is no cosmic neighborhood watch, no shared archive of knowledge drifting conveniently between stars. Each system is on its own. That isolation has consequences. In environments where systems are connected, complexity can spread. Innovations propagate. Failures can be compensated for by external support. In biology, ecosystems thrive on interaction. In human societies, progress depends on exchange. The universe offers none of that by default. If life arises on a planet, it must survive local hazards without help. Stellar flares, asteroid impacts, climate instability, geological upheaval, radiation, timescales that dwarf biological resilience. If it fails, there is no backup copy arriving from elsewhere. The silence between stars ensures that mistakes are permanent. This is part of what makes the emptiness feel ominous. It suggests not just rarity but fragility. When we imagine a universe teeming with life, we often imagine it as noisy. Signals everywhere, evidence everywhere. But noise requires density. It requires proximity. It requires overlap. A sparse universe suppresses noise. Even if life is common relative to the number of planets, the distances involved ensure that evidence remains hidden. Silence in this sense does not prove absence, but it does amplify vulnerability. Consider how thin the margin is on Earth. Life here depends on a narrow temperature range, liquid water, stable orbits, and a protective magnetic field. Small changes in any of these could render the planet sterile, and yet, from a cosmic perspective, Earth sits in a relatively calm region, not too close to the galactic centre, not too far out, not orbiting a volatile star. Even so, extinction events have nearly reset the biosphere multiple times. Now scale that up. Imagine countless planets scattered across the universe, each facing their own local challenges, each isolated by light years of emptiness. Some may develop life, fewer develop complex life, fewer still develop intelligence capable of technology, and at every stage failure is far more likely than success. The silence between stars may be telling us something uncomfortable. Not that life never arises, but that it rarely lasts long enough to matter beyond its immediate surroundings. There is another layer to this silence that's easy to overlook. Time. The universe is not just spatially empty, it is temporally sparse. Events of significance are separated by immense durations. Stars live for millions to billions of years, but intelligent civilizations, if our own history is any guide, may exist for only thousands or tens of thousands of years. That is a blink of an eye compared to cosmic timescales. Two civilizations could arise in the same galaxy and never overlap in time. One could flourish and vanish before the other even begins. From the outside, the galaxy would appear silent throughout. The gaps between stars hide not just distance, but missed connections. When you combine spatial isolation with temporal mismatch, the probability of meaningful contact drops dramatically. Even if the universe produces intelligent life repeatedly, the conditions required for overlap are strict. Same region, same time, sufficient longevity, technological capability, motivation to communicate. The silence we observe may be the natural outcome of these compounded constraints, and this brings us back to the experience of looking up at the night sky. That quiet moment where the stars feel close, but something about the darkness between them feels heavy. Not threatening exactly, but indifferent, unmoved by our attention. The universe does not announce itself. It does not reassure. It does not fill the gaps for our comfort. It leaves space as space, empty, expanding, unconcerned. This can feel unsettling if we expect the universe to be welcoming, but it can also be clarifying. Emptiness simplifies things, it strips away assumptions. It forces us to confront how unusual our situation is. A small planet orbiting a stable star in a region where heavy elements exist, at a time when the universe is still young enough to support complexity. That combination is not guaranteed. It is not widespread. It may be fleeting. The silence between stars is not just a lack of sound or signal. It is a reminder of scale, probability, and isolation. It sets the stage for the deeper question we're moving toward. Not just why the universe is empty, but what that emptiness implies about survival, persistence, and the odds stacked against anything that tries to endure. The first time most people encounter the true scale of emptiness in space, it doesn't come from looking through a telescope or watching a documentary. It comes from a number, a comparison, a realization that lands quietly and then refuses to leave. Up until that moment, space feels big, sure, but still imaginable. After it, the word empty never quite means the same thing again. To get there, we have to strip away intuition, because intuition evolved for forests, plains, and shorelines, not for vacuum stretched across billions of light years. Your brain is excellent at judging distances measured in steps, streets, even continents. It fails badly when the distances grow beyond anything you can experience directly. So let's start somewhere familiar. Picture the room you're in right now. The air around you feels solid enough. You can feel it move when you wave your hand. You know it's full of molecules bouncing, colliding, transferring heat and sound. Even when a room feels still, it is busy beyond imagining. Now remove the air. True empty space is not like a quiet room. It is not even like a high-altitude mountaintop. It is a vacuum so extreme that comparing it to anything on Earth becomes misleading. In interstellar space, the average density is about 1 atom per cubic centimetre. Sometimes less. Often much less. A cubic centimetre is about the size of a sugar cube. Inside that cube of space, on average, there is one lonely atom. Sometimes it's hydrogen. Sometimes nothing at all for long stretches. That's it. No air, no pressure, no sound, no meaningful friction. Just isolated particles drifting vast distances before encountering anything else. If you compare that to the air you're breathing now, the difference is staggering. Air at sea level contains roughly 10 quintillion molecules per cubic centimetre. That's a 1 followed by 19 zeros. The gap between those numbers is not just large, it's absurd. And interstellar space is considered relatively crowded. Once you move into the vast regions between galaxies, the density drops further. In cosmic voids, there may be only a few atoms per cubic metre. Entire volumes the size of buildings contain less matter than the tip of a pin. These are not special locations, they make up most of the universe by volume. This is the first real shock. Not that space is empty, but that it is empty to a degree that borders on total absence. Even objects we think of as solid contributors to the universe barely register. Stars, for all their mass and brightness, occupy almost none of the universe's volume. Galaxies themselves are mostly empty space. The solar system is mostly empty space. At every scale, matter clumps into tiny islands surrounded by enormous voids. If you were to shrink the solar system down so that the sun were the size of a marble, Earth would be a grain of sand several meters away. Jupiter would be another marble tens of meters out. Beyond that, nothing for a very long distance. And this pattern repeats outward, scale after scale. What's unsettling is how counterintuitive this is. We grow up with images of space filled with swirling nebulae, glowing clouds, colourful galaxies packed tightly together. These images are real, but they are misleading. They show the highlights, the exceptions, the rare regions where matter happens to be dense enough to glow. Most of space would look completely black, even with extremely sensitive instruments. No colour, no structure, no obvious landmarks. And this emptiness is not static. As the universe expands, space itself stretches. The same amount of matter occupies more and more volume. Over time, average densities decrease. Regions that are empty now will become emptier still. The universe is not heading toward balance, it is heading toward dilution. This leads to a subtle but important realization. The universe is not empty because matter failed to fill it. It is empty because space outpaces matter. Expansion does not slow down to let things catch up. On the larger scales, it accelerates. Dark energy, whatever its precise nature, ensures that distant regions move away from each other faster and faster. Gravity can hold galaxies together locally, but it cannot stop the overall stretching. As a result, isolation increases with time. Galaxies beyond a certain distance are already receding faster than light relative to us, not because they are breaking a speed limit, but because the space between us and them is expanding. Their light will never reach us. They're gone from our observable universe, not by destruction, but by separation. In the far future, even nearby galaxies will slip away. Observers will see less and less of the cosmos. The universe will appear emptier than it already does. This is the second shock. Emptiness is not just a present condition. It is the direction things are moving. At this point, it's tempting to ask whether emptiness really matters. After all, if matter clumps where it needs to, maybe the empty parts are irrelevant. Maybe life only needs small pockets of activity. Maybe the rest is just unused space. That idea doesn't survive contact with physics. Empty space is not neutral. It shapes everything around it. It determines how forces propagate, how energy spreads, how structures interact. In a dense universe, interactions would be frequent. In a sparse one, they are rare. This affects everything from star formation to chemical enrichment. Heavy elements, the building blocks of planets and life, are forged in stars and distributed through explosions. In a dense environment, those materials would mix efficiently. In our universe, they disperse slowly, unevenly, often missing entire regions entirely. Many galaxies never receive enough heavy elements to form rocky planets. Many star systems form in isolation, with limited chemical diversity. The emptiness acts as a bottleneck, limiting what can form and where. It also affects time. In dense systems, processes happen quickly. Collisions, interactions, feedback loops. In empty systems, everything slows down. Encounters are rare. Change takes longer. Energy dissipates slowly into nothingness. This creates an uneven universe, where some regions evolve rapidly and others barely evolve at all. Life, which depends on a steady but not overwhelming flow of energy and material, finds itself squeezed into narrow windows. Too dense and environments become violent, too empty and nothing happens. Earth sits in a middle ground that is not common. The shock deepens when you realize that even matter itself is mostly empty. At the atomic level, atoms are almost entirely void. Nuclei occupy tiny regions compared to the space taken up by electron clouds. The solidity you experience is a result of electromagnetic forces, not physical contact. From atoms to solar systems to galaxies, emptiness is the rule. This raises an uncomfortable question. If emptiness dominates at every scale, why does anything complex exist at all? The answer is that complexity is not favoured. It is tolerated briefly under the right conditions. Those conditions arise naturally in some places, but they are unstable and temporary. Stars burn fuel and die. Planetary orbits shift. Radiation accumulates. Entropy increases. Over long timescales, the universe erases structure. Empty space is not passive. It is the end state. Another way to feel the scale of emptiness is to consider probability. Imagine randomly selecting a point in the universe. The chance that it lands inside a star is effectively zero. Inside a planet, even smaller. Inside a living organism, vanishingly small. Almost every random point lies in intergalactic void. From the universe's perspective, life is negligible, not in value, but in presence. This is where the idea of a terrifying reason begins to take shape. The emptiness suggests not just rarity, but indifference. The universe does not arrange itself to maximize complexity or awareness. It expands, it cools, it smooths out differences. Anything that resists that trend must do so locally and temporarily, constantly fighting a losing battle. When we look at the sky and see stars scattered across blackness, we are seeing the survivors of a process that eliminates most structure before it ever begins. Each star represents a region where conditions happen to align long enough for fusion to ignite. Each planet represents an even narrower alignment. Life narrows the odds further. Intelligence narrows them further still. The emptiness is not evidence of design or malice. It is evidence of scale, of a universe where the default state is nothing and something requires explanation. This reframes many familiar questions. Instead of asking why we haven't found others yet, we can ask why anything found us at all. Instead of assuming the universe is crowded and strangely quiet, we can consider that it may be exactly as full as physics allows. Silence in this context is not mysterious. It is expected. As you sit with this, it's normal to feel a sense of distance. Not just physical distance, but conceptual distance. The universe feels less like a place you could explore, and more like a vast process unfolding without reference to observers. That feeling is part of the shock, but it's also a starting point. Because once you accept how empty space really is, you can begin to ask more precise questions. How does structure emerge at all? Why do galaxies form where they do? What role do unseen components like dark matter play in shaping the sparse architecture of the universe? And perhaps most importantly, what does this level of emptiness imply about how fragile our own existence might be? At the very beginning, the universe did not resemble the place we see today. There were no stars scattered across blackness, no galaxies drifting apart, no immense voids swallowing most of reality. Instead, everything was close, uncomfortably close. Matter, energy, radiation, all packed together in a state so hot and dense that the concepts of empty and full barely applied. This is an important starting point, because it overturns a quiet assumption many people carry without realizing it. The universe did not begin empty and slowly fill up. It began crowded, almost uniformly so, and then spent billions of years thinning itself out. Shortly after the Big Bang, the universe was a nearly smooth soup of particles and light. Not smooth in the sense of calm, but smooth in distribution. There were no stars or planets yet, but there also were no vast voids. Everywhere you looked, conditions were almost the same. Temperature, density, energy, all varied only slightly from place to place. Those slight variations mattered more than anything that followed. Tiny differences in density, far too small to notice without sensitive measurements, acted as seeds. Regions that were just a little denser than average exerted slightly more gravitational pull. Over time, those regions began attracting more matter. Not quickly, not dramatically, just enough to start a feedback loop. Gravity is patient. As the universe expanded and cooled, these denser regions grew denser still, while slightly emptier regions lost matter and became emptier. This process did not create neat, evenly spaced objects. It created contrast, peaks and valleys, areas where matter collected and areas where it drained away. Over hundreds of millions of years, this slow imbalance produced the first large-scale structures. Gas clouds collapsed into the first stars. Stars grouped into primitive galaxies. Those galaxies began clustering along invisible scaffolding, defined largely by dark matter, forming filaments and nodes. At this stage, the universe was still comparatively busy. Star formation rates were high. Collisions between galaxies were common. Gas was abundant. Heavy elements were being forged and scattered at an accelerating pace. From a distance, this era would have looked energetic, active, almost chaotic. But it did not last. As time moved forward, several trends began working against complexity. Expansion continued, stretching space and reducing average density. Gas supplies were gradually locked up in stars or expelled by violent events. Radiation from early generations of stars altered surrounding environments, making some regions less hospitable to further star formation. The universe was not settling into equilibrium, it was transitioning. Galaxies continued to grow, but their growth slowed. Star formation peaked and then began to decline. Regions that missed the early wave of structure formation found themselves at a disadvantage. Without enough mass early on, they could not compete gravitationally. Matter flowed away from them toward denser regions, leaving behind growing voids. This is where cosmic loneliness begins to emerge. As galaxies clustered, the spaces between those clusters expanded faster than gravity could bridge. Distances increased. Interactions became less frequent. Systems that once might have collided now drifted apart permanently. The universe was not just expanding, it was separating. Over time, this separation became self-reinforcing. The more isolated a region became, the less opportunity it had to gain new material or energy. Star formation dwindled, chemical enrichment slowed. The chances of complex structures arising dropped sharply. Loneliness, in this sense, is not emotional. It is statistical. The universe moved from a state where matter was everywhere to a state where matter was confined to fewer and fewer places. Those places became islands, surrounded by expanding oceans of emptiness, and this process continues today. When astronomers observe distant galaxies, they are looking back in time. Light from those objects left when the universe was younger, denser, and more active. Compared to the present, the early universe was brighter, more crowded, and more productive. Stars formed faster, galaxies interacted more often, the cosmic web was tighter. As time passed, the web stretched, filaments thinned, nodes grew more isolated. Eventually, even galaxies within the same cluster will lose contact with each other. Expansion will carry them apart beyond communication. What remains will be local systems, bound by gravity, surrounded by an ever-growing darkness. This trajectory is not subtle. It is one of the most fundamental features of cosmic history. What makes it unsettling is how directly it impacts the possibility of life. Life does not require a crowded universe, but it does benefit from a universe that recycles materials efficiently. Heavy elements must be produced and distributed. Planets must form from enriched gas. Stable environments must persist long enough for chemistry to become biology. All of these processes depend on interactions. In a crowded universe, interactions are common. Material mixes, energy flows, information spreads, at least in a physical sense. In a lonely universe, everything happens in isolation. Each system gets one shot. Earth exists because our region of the universe formed at a time and place where conditions were still favourable. Enough stars had lived and died to produce heavy elements. Enough gas remained to form new stars and planets. The environment was calm enough for long-term stability. That combination is not guaranteed indefinitely. As the universe continues to thin, the window for forming new habitable worlds narrows. Future generations of stars will have less material to work with. Regions that never formed galaxies early on may never form them at all. Chemical complexity becomes harder to achieve. The universe is not just lonely now, it is becoming lonelier. This is where the idea of a terrifying reason starts to sharpen. The emptiness we observe is not simply a snapshot. It is the result of a long trend away from connection, toward separation, toward isolation at every scale. From the crowded beginnings of the cosmos, where everything influenced everything else, we have arrived at a stage where influence barely travels, and that has consequences beyond astronomy. If intelligent life arises in such a universe, it does so under increasing pressure. It must survive locally. It must solve its own problems. It cannot rely on help from elsewhere. Even communication across cosmic distances becomes impractical. Failures do not propagate, but neither do successes. This isolation means that extinction is final, not just locally, but cosmically. A civilization that collapses leaves no trace beyond its immediate surroundings. Its knowledge, its culture, its achievements vanish into silence. Over billions of years, this pattern could repeat many times. The universe does not record its experiments. From this perspective, the emptiness is not just physical, it is historical. It reflects a universe that does not preserve complexity well, one that allows brief islands of structure to form, flourish briefly, and then fade without replacement. The early universe may have been crowded, but it was also unstable. High-energy environments are hostile in their own way. Radiation was intense. Conditions changed rapidly. Long-term stability was rare. The middle-aged universe where we now find ourselves offers a temporary balance. Expansion has cooled things enough for stability, but not so much that isolation dominates completely. That balance will not last forever. In the far future, the universe will be quieter still. Star formation will slow to a crawl. Galaxies will exhaust their fuel. The night sky, from any remaining vantage point, will grow darker as distant galaxies disappear beyond the cosmic horizon. Observers, if any remain, will inhabit a universe that appears far emptier than ours does now. From crowded beginnings to cosmic loneliness, the trajectory is clear. The universe is moving away from interaction, away from density, away from connection. This does not make existence meaningless, but it does make it precarious. It suggests that complexity is a temporary rebellion against a long-term trend, a flicker that appears under the right conditions and fades when those conditions pass. Understanding this shift helps reframe many of the questions we ask about life in the universe. It encourages us to think less in terms of abundance and more in terms of timing, less about why there is so little and more about why there is anything at all. At first glance, stars appear scattered almost playfully across the sky, as if someone tossed handfuls of light into the darkness without much concern for spacing. Some cluster together in familiar patterns, others stand alone, and from Earth's surface it's easy to assume that these points of light are part of a relatively tight arrangement, a kind of cosmic neighbourhood where distances are large but not absurd. That assumption collapses the moment you look beyond appearances. Stars are not far apart by accident, and they are not spaced that way because the universe ran out of room. They are far apart because the processes that create them demand distance, and because the universe actively works against keeping them close. The spacing between stars is not a flaw in the cosmic design. It is a requirement enforced by physics over billions of years. To understand why, it helps to start with how stars form in the first place. Stars are born inside clouds of gas and dust known as molecular clouds. These clouds can be enormous, spanning hundreds of light years, and they are among the densest structures in galaxies. Even so, calling them dense is relative. Compared to air on Earth, they are still extremely sparse. What makes them special is not how packed they are, but how cold and massive they are. Within these clouds, small regions can become slightly denser than their surroundings. If a region gathers enough mass, gravity begins to pull it inward. As it collapses, it heats up. Eventually, if conditions are right, nuclear fusion ignites in the core and a star is born. This process is slow and inefficient. Most of the material in a molecular cloud never becomes part of a star. It remains gas, gets blown away by radiation, or drifts off into interstellar space. Only a small fraction ends up locked inside stellar cores, and crucially, stars do not form arbitrarily close together. As soon as a star ignites, it begins to affect its surroundings. Radiation pours out. Stellar winds push gas away. If the star is massive, it may emit intense ultraviolet light that ionizes nearby material, heating it and preventing further collapse. In effect, each newborn star clears out a region around itself. This creates a natural spacing mechanism. When one star forms, it suppresses the formation of nearby stars for a time. In dense regions, this leads to clusters, but even there, stars maintain significant distances from one another. In less dense regions, it leads to isolation. The available gas gets used up or dispersed before another star can form nearby. Over time, this feedback ensures that stars are never packed together tightly on average. Now add another layer: motion. Stars are not stationary. Once they form, they orbit the center of their galaxy. They move relative to one another. Over millions and billions of years, these motions stretch out initial groupings. Star clusters disperse, associations dissolve. Individual stars drift into new orbits, separated by ever-increasing distances. Gravity holds galaxies together, but it does not enforce local crowding. In fact, stable orbits tend to keep stars apart rather than pulling them closer. In our region of the Milky Way, the average distance between stars is several light-years. That means that even the closest neighbouring stars are so far away that light itself takes years to travel between them. Any slower signal, or any physical object, would take vastly longer. This distance is not unusual. It is typical. From the universe's perspective, stars are rare events. They are luminous, massive, and important, but they occupy almost none of the available space. The volume of a galaxy is dominated not by stars but by emptiness. This leads to a natural question. Why didn't gravity pull everything closer together? Why didn't the early universe collapse into dense clusters everywhere? The answer lies in balance. Gravity is strong locally, but it is slow to act over large distances. Expansion, on the other hand, operates everywhere at once. In the early universe, expansion was rapid. Matter had limited time to clump before space stretched further. Only regions that started slightly denser than average could overcome this expansion locally. Everywhere else, matter thinned out. Even in regions where stars formed, gravity never fully won. It only carved out islands. These islands did not merge into continents. Another factor is angular momentum. Gas clouds rotate, even if only slightly. As they collapse, that rotation speeds up, flattening material into disks and preventing everything from falling straight inward. Angular momentum acts as a barrier, limiting how compact structures can become. This is why planetary systems form as flat disks, and why stars don't collapse endlessly into single points. Rotation enforces separation. Then there is energy. When matter falls together under gravity, it releases energy. That energy has to go somewhere. In star formation, it heats the gas, increasing pressure and slowing further collapse. If too much energy builds up, collapse stops entirely. This self-regulating behaviour ensures that star formation never runs away completely. The universe produces stars, but it limits how many and how close together they can be. All of this explains why stars form with spacing built in, but it doesn't yet explain why those distances remain so large over cosmic time. For that, we need to consider the broader environment. Galaxies themselves are moving apart as the universe expands. While gravity binds stars within a galaxy, it does not counteract expansion on intergalactic scales. Galaxies drift away from one another, and with them, their stellar populations become increasingly isolated. Even within galaxies, interactions that might bring stars closer together are rare. Direct stellar collisions are extraordinarily uncommon. The distances are simply too great. A star could orbit the galaxy for billions of years without coming anywhere near another star. This has an important implication. The universe is not built for interaction at the scale of stars. It is built for separation. That separation acts as both protection and limitation. On one hand, the vast distances between stars make collisions unlikely. Planetary systems can remain stable for long periods. Life has time to evolve without constant disruption. If stars were packed closer together, environments would be far more hostile. Radiation levels would be higher. Gravitational disturbances would be frequent. Orbits would be unstable. In that sense, distance is a feature, not a bug. On the other hand, that same distance makes cooperation impossible. It prevents easy exchange of material and information. It isolates systems from one another. Whatever happens around one star has almost no effect on its neighbours. For life, this is a double-edged situation. Life requires stability, but it also benefits from diversity and exchange. On Earth, ecosystems thrive on interaction. Species migrate, genes mix, resources flow. Isolation tends to reduce resilience. At the cosmic scale, isolation is extreme. If life arises around a star, it does so alone. If it develops technology, it develops it without outside input. If it fails, there is no rescue. If it succeeds, there is no audience. The distances between stars ensure that civilizations, even if common, are effectively quarantined from one another. This begins to hint at the darker interpretation of emptiness. Stars are far apart not because the universe wanted room to breathe, but because the processes that create structure cannot overcome expansion, energy feedback, and angular momentum at large scales. The universe allows complexity only in diluted form. It builds sparks, not fires. There is another aspect worth considering. Time again. Stars have lifespans measured in millions to billions of years. Civilizations, as far as we know, do not. The overlap between technological societies around different stars would require not just proximity, but timing. Given distances of several light years, even communication takes years. Travel takes far longer. If one civilization rises and falls within a few thousand years, and another appears tens of thousands of years later around a different star, they may as well exist in different universes. The spacing between stars magnifies this temporal mismatch. Even if life were common, the chances of two civilizations being close enough in space and overlapping enough in time to interact meaningfully are low. The stars are far apart, and that fact quietly stacks the odds against connection. When astronomers search for signals from other civilizations, they are listening across these vast distances. Every year without detection does not necessarily mean no one is out there. It may simply reflect the brutal geometry of the cosmos. Sparse stars mean sparse opportunities. It's also worth noting that the spacing between stars has increased over time. In the early universe, galaxies were more compact. Stars were closer together. Interactions were more frequent. That period may have been more favourable for exchange, but also more violent. High-energy radiation, frequent supernovae, and gravitational chaos may have made stable life harder to sustain. As the universe aged, conditions became calmer, but also lonelier. This suggests that there may have been a narrow window, where stars were close enough to allow interaction, but calm enough to allow stability. That window may have been brief. It may already be closing. From this perspective, the distance between stars is not just a measurement. It is a constraint, a quiet rule that shapes everything that follows. It determines how galaxies evolve, how planets remain stable, how life survives, how civilizations remain isolated. When you look up at the night sky and see stars scattered across darkness, you're seeing the result of countless physical processes conspiring to keep things apart. Gravity builds locally, expansion stretches globally, energy and motion regulate collapse, time amplifies separation. The universe does not clump generously, it rations structure. This is not terrifying in a dramatic sense. There is no immediate threat implied by the distance between stars, but it is unsettling in a quieter way. It suggests that the universe is not arranged to foster connection. It allows islands but discourages bridges. When you first learn about galaxies, they're often presented as majestic collections of stars, swirling gracefully through space, vast but coherent, like cities of light scattered across the cosmos. Spiral arms curve elegantly. Ellipticals glow softly. Irregular galaxies look chaotic but lively. It's easy to focus on what's inside them and forget to ask a quieter, more unsettling question. What lies between them? Galaxies are not just large objects floating near one another. They are profoundly isolated systems, separated by distances so extreme that even light struggles to bridge them in any meaningful way. They are not neighbours in the way towns or even stars are neighbours. They are islands, and the ocean between them is not calm, not static, and not shrinking. It is expanding. To understand why this matters, it helps to zoom out again, not emotionally, but mechanically. A galaxy is bound together by gravity. Stars orbit a common centre. Gas clouds move within a shared gravitational well. Dark matter forms a massive invisible halo that holds the whole structure together. Inside that boundary, gravity dominates. Expansion does not tear galaxies apart. Your Milky Way is not slowly stretching from the inside. The stars within it are not drifting away because of cosmic expansion, but beyond that boundary, gravity loses. On the largest scales, the universe expands relentlessly. Space itself stretches, and anything not tightly bound by gravity is carried along with it. Galaxies outside of clusters, clusters outside of superclusters, all drift apart as the cosmic fabric lengthens between them. This is not a subtle effect. It defines the large-scale fate of the universe. If you imagine placing markers throughout space, those markers move apart over time, not because they're travelling through space, but because space itself is growing. The farther apart two galaxies are, the faster the space between them expands. At great enough distances that expansion exceeds the speed of light, making communication permanently impossible. This is how galaxies become islands. In the early universe, galaxies were closer together. Interactions were common. Collisions and mergers shaped their evolution. Star formation was fueled by abundant gas pulled in from surrounding regions. The cosmic web was tight, with filaments feeding material into growing structures. As time passed, that web stretched. Filaments thinned. Voids widened. Galaxies that were once part of interconnected systems became increasingly isolated. Some merged into clusters, forming local archipelagos, but even these clusters are surrounded by growing expanses of emptiness. Our local group, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies, is gravitationally bound. Andromeda will eventually merge with the Milky Way. Within this small region, gravity still wins. Beyond it, the universe pulls everything apart. Galaxies outside our local group are already receding from us. The farther away they are, the faster they recede. This relationship, first observed by Edwin Hubble, is not about motion through space, but expansion of space. And it has a chilling implication. There is a horizon beyond which we cannot see or influence anything, not because of technological limits, but because of geometry. Light emitted today by sufficiently distant galaxies will never reach us. Space expands too quickly in between. Those galaxies fade from our observable universe not by destruction, but by disconnection. Over time, this horizon moves inward. Galaxies that are visible now will eventually cross it. Their light will stretch, redshift, weaken, and finally vanish. The universe will appear emptier not because matter is gone, but because it is unreachable. This means that cosmic loneliness increases with time. In the far future, observers inside galaxies like ours will see only their local cluster. Everything else will have disappeared beyond the horizon. The cosmic microwave background will fade. Evidence of the Big Bang itself will become undetectable. The universe will look static, dark, and small. From inside such a future galaxy, it would be reasonable to conclude that the universe contains almost nothing. This isolation is not just observational. It has physical consequences. Galaxies grow and evolve through interaction. When they collide or pass near one another, gases compress, triggering bursts of star formation. Material is exchanged. Structures are reshaped. These interactions are engines of complexity. As galaxies become isolated, these engines shut down. Star formation slows. Gas supplies are exhausted or heated. Without fresh material flowing in from the cosmic web, galaxies age. Their stellar populations grow older. Bright, massive stars die off. What remains are long-lived, dim stars and stellar remnants. Elliptical galaxies, often found in dense clusters, are examples of this end state. They contain old stars, little gas, and minimal ongoing star formation. They are quiet systems, no longer building much of anything new. Isolation accelerates this quieting. This is one reason the emptiness of the universe feels unsettling. It is not just empty now. It is becoming quieter, less productive, less dynamic. From the perspective of life, this matters deeply. Life depends on stars, but it also depends on generations of stars. Heavy elements like carbon, oxygen, nitrogen, and iron are forged in stellar cores and distributed through supernovae and stellar winds. These elements must mix into new star-forming regions to create rocky planets and complex chemistry. In a connected universe, this recycling happens efficiently. In an isolated one, it becomes patchy. Some galaxies may never receive enough heavy elements to form Earth-like planets. Others may form them only early on. Over time, the raw materials for life become locked away in dead stars and compact remnants. The expanding sea between galaxies acts like a barrier to enrichment. This introduces a quiet filter on habitability. Not all galaxies are equally capable of supporting life, and that capability changes over time. The longer a galaxy remains isolated, the less likely it is to host new habitable worlds. Even within galaxies that do host life, the island nature of galaxies imposes limits on survival beyond local scales. If a catastrophic event wipes out life in one galaxy, there is no replenishment from elsewhere, no migration of biology across intergalactic space. The distances are too vast, the timescales too long. Life either persists locally or it ends entirely. This applies equally to intelligent life. Civilizations, if they arise, are confined to their galactic islands. Even if they master interstellar travel within a galaxy, intergalactic travel remains an almost insurmountable challenge. The energy required is staggering. The journey times extend far beyond biological lifespans. The target itself may be receding faster than any ship could follow. This means that the universe is not a single connected arena where progress accumulates. It is a collection of isolated experiments, each running independently, each unaware of the others. Failures do not inform successes. Successes do not spread. From a certain angle, this makes the universe feel wasteful. So much space, so much time, so little interaction. But from a physical standpoint, it is simply how expansion works. Dark energy, whatever its underlying nature, ensures that the expansion of the universe accelerates. This acceleration overwhelms gravity on large scales. Structures that are not already bound drift apart forever. Galaxies are the largest stable units. Everything larger dissolves into separation. This realization reframes the emptiness we see. It is not just the absence of matter. It is the consequence of a universe that prioritizes expansion over cohesion. When we say galaxies are islands, we're not using a metaphor loosely. The comparison is precise. Islands are defined not just by what they contain, but by what separates them. The sea limits travel. It limits exchange. It enforces independence. The cosmic sea does the same, but more effectively. There is no intergalactic equivalent of trade winds or currents that ease passage. There is only expansion, pulling everything farther apart. Even information struggles. Signals weaken. Delays grow. Eventually silence becomes permanent. This has a subtle psychological effect when you really let it sink in. It means that the universe does not feel crowded once you understand it. It feels fragmented, disconnected, as if reality itself has been partitioned into countless sealed compartments, and each compartment is on its own clock. Some galaxies formed early and burned brightly, others formed late and slowly. Some may never form stars at all. Their histories do not synchronize. Their peaks of activity do not align. This temporal isolation compounds spatial isolation. Two galaxies might both host life at some point in their histories, but never at the same time, or one might host life only after the other has gone dark. From the universe's perspective, these events do not overlap. The silence persists. This brings us closer to the unsettling implication that the universe may not just be empty of life, but empty of continuity. Complex structures arise, persist briefly, and fade without leaving lasting influence beyond their local island. The expanding sea ensures that nothing ties these stories together. When you look at images of deep space, with galaxies scattered across blackness, it can feel inspiring. Each galaxy, a world unto itself, each one full of stars, perhaps planets, perhaps life. That inspiration is real, but incomplete. What those images also show, if you look long enough, is separation, the overwhelming dominance of darkness. The fact that galaxies do not cluster into something larger and enduring, but drift apart into increasing solitude. The universe does not gather, it disperses. This dispersal is slow enough that we can ignore it day to day, slow enough that civilizations might rise and fall without ever noticing it directly, but it is fast enough to define the ultimate limits of connection. As we move forward, this pattern will only intensify. The sea will widen, the islands will shrink in relevance. The universe will trend toward a state where each remaining structure exists in practical isolation, surrounded by darkness that grows deeper with time. Understanding galaxies as islands is not meant to diminish their beauty. It is meant to clarify their role. They are refugees of structure in a universe that increasingly favours emptiness. For most of human history, space was imagined as a static stage. Stars moved across it, planets traced paths through it, but the stage itself was assumed to be fixed, unmoving, eternal. Even when astronomers began to understand the immense scale of the universe, the underlying assumption lingered quietly in the background. Space was just there, waiting patiently while things happened inside it. That assumption turned out to be wrong in a fundamental way. Space is not passive, it does not sit still, it stretches. This realization did not arrive with drama at first. It emerged slowly through careful measurements and an uncomfortable pattern that refused to go away. When astronomers in the early 20th century began measuring the light from distant galaxies, they noticed something odd. Almost all of those galaxies showed the same feature in their spectra. Their light was shifted toward the red end of the spectrum, redshift. At first, this seemed like a technical curiosity. Then the pattern became undeniable. The farther away a galaxy was, the more its light was redshifted. Distance and redshift were linked. Edwin Hubble formalized this relationship, and with it, the universe quietly changed forever. The galaxies were not simply moving through space away from us. Space itself was expanding, carrying them along. This distinction matters deeply. If galaxies were flying through space like debris from an explosion, gravity might eventually slow them down. They might collide again. The universe could, in principle, reconverge, but that is not what expansion means. Expansion means that the distance between objects increases, even if the objects themselves are not moving locally. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, even though none of them is actively crawling away from the others. The surface itself is stretching. That is what space does. Once this idea is accepted, the growing emptiness of the universe stops being a mystery and starts looking inevitable. As space stretches, matter thins. The same amount of material occupies more volume. Density drops. Interactions become rarer. Regions that were once close enough to influence each other drift beyond reach. This stretching has been happening since the universe began, but it has not been constant. In the early universe, expansion was rapid, but gravity was strong enough to slow it down somewhat. Matter was dense. Structures could still form. Galaxies grew. Clusters assembled. The cosmic web tightened. Then something changed. Several billion years ago, the expansion of the universe began to accelerate. This was not predicted by classical physics. In fact, many scientists expected the expansion to slow indefinitely, perhaps even reverse. Instead, careful observations of distant supernovae revealed that galaxies were not just receding, but receding faster than expected. The expansion rate was increasing. The cause of this acceleration was given a name that reflects our ignorance rather than our understanding: dark energy. Dark energy is not something we can see directly. It does not clump like matter. It does not emit light. It does not interact strongly with anything we can easily detect. What it does apparently is drive space to expand faster and faster over time, and it dominates the universe. Roughly 70% of the universe's total energy content appears to be dark energy. Matter, both ordinary and dark, makes up the remaining 30%. Of that, ordinary matter, the kind that forms stars and planets and people, accounts for only a few percent. This imbalance has profound consequences. As dark energy pushes space to expand, gravity becomes less effective at large scales. Structures that are already bound remain intact, but nothing new binds beyond them. The universe transitions from a state where structure formation is common to one where separation dominates. This is the great stretch. The growing voids between galaxies are not simply empty regions left behind by matter clustering elsewhere. They are regions actively being expanded, diluted, and isolated by the accelerating growth of space itself. Over time, this process creates a universe where interactions become increasingly local. Galaxies talk only to their nearest neighbours. Clusters become isolated. Eventually, even clusters become lonely. The voids grow, not just in size, but in significance. Consider what happens to a photon travelling through expanding space. As space stretches, the wavelength of the photon stretches with it. The photon loses energy. Its light reddens. Over extreme distances, it fades into invisibility. This is not because the photon is tired, or because something absorbs it. It is because the space it traverses grows while it is in transit. This effect ensures that distant regions of the universe become not only unreachable, but undetectable. They are still there, but functionally erased from view. The observable universe shrinks relative to the total universe. From our perspective, the void grows darker and deeper. This process also affects matter itself. Gas clouds become more diffuse. Regions that might once have formed stars no longer have the density required to collapse. Expansion works against gravity continuously, and gravity loses more ground as time goes on. Star formation rates decline. This decline is already well underway. The universe today forms stars at a fraction of the rate it did billions of years ago. Most of the stars that will ever exist have already been born. The remaining gas is either locked up in existing stars or spread too thin to collapse efficiently. As expansion accelerates, this trend continues. The future universe is not one of renewal. It is one of gradual exhaustion. This is where the growing void becomes more than a geometric feature. It becomes a defining condition. In a universe dominated by voids, the opportunities for complexity decrease over time. Not because laws of physics change, but because the environment becomes less favourable. Energy sources fade, material becomes scarce, distances grow, life, which depends on gradients, flows and recycling, finds fewer places to persist. The Great Stretch does not destroy structures violently, it erodes them quietly. There is no dramatic tearing of galaxies, no sudden collapse into darkness. Instead, there is a long fading, a thinning out, a drift toward isolation so complete that even the memory of a crowded universe disappears. If intelligent observers exist far in the future, they may not know the universe was ever larger or richer than what they see. Expansion will have erased the evidence. The cosmic microwave background will be undetectable. Distant galaxies will be gone. The idea of a Big Bang may seem unsupported or unnecessary. They will live in a universe that appears static, empty, and old. This has led some physicists to describe the future cosmos as a kind of cosmic loneliness, not just spatially, but informationally. Knowledge itself becomes localized. History fades beyond horizons. From this perspective, the terrifying reason the universe is so empty is not that it lacks material, but that it is actively pushing material apart. The void is not waiting. It is growing, and it grows faster with time. This is a difficult idea to absorb because it runs counter to everyday experience. On Earth, expansion is something we associate with filling space. Gases expand into containers. Populations expand into available land. Expansion feels like growth. Cosmic expansion is the opposite. It creates room faster than anything can fill it. The result is a universe where emptiness increases even as structures persist locally. Islands remain, but the ocean between them widens without limit. This widening has another consequence that often goes unnoticed. It limits causality. There are events happening right now, somewhere in the universe, that will never affect us, not because of shielding or distance alone, but because the space between us and them expands too quickly for any signal to cross. Those events might as well not exist as far as we're concerned. Causality itself becomes regional. This fragmentation of reality into causally disconnected regions is one of the most unsettling implications of accelerated expansion. It means that the universe is not a single shared stage. It is a collection of separate arenas, each with its own future. Within each arena, physics plays out normally. Stars burn, planets orbit. Life may arise. But beyond the horizon, nothing matters. The growing void enforces this separation. As we consider the emptiness of the universe, it becomes clear that it is not merely a leftover from formation. It is the dominant outcome of expansion driven by dark energy, a long-term trend toward isolation, dilution, and silence. This does not mean that the universe is hostile in a deliberate sense. It is not targeting life or complexity. It is simply following rules that do not prioritize connection. The great stretch is impartial, yet its consequences are not. For any structure that depends on interaction, on exchange, on continuity, accelerated expansion is a limiting factor. It ensures that whatever exists must make do with what it has locally. There will be no cosmic rescue, no universal convergence, no late-stage collaboration across vast distances. Everything that matters happens on small scales, briefly, against a background that grows more indifferent with time. For a long time, astronomers believed they had a reasonably complete picture of what held the universe together. Stars orbited galaxies because of gravity. Galaxies moved within clusters because of gravity. Everything that mattered, it seemed, could be explained by the mass we could see. Light traced matter, matter traced structure. The universe, though vast and empty, at least played by visible rules. That confidence didn't survive careful measurement. The first cracks appeared quietly. Galaxies rotated too fast. Stars at their edges moved as if far more mass were present than telescopes could detect. According to the laws of gravity, those stars should have flown off into space. They didn't. Something unseen was holding them in place. At first, this discrepancy was treated as a problem to be solved locally. Maybe measurements were wrong. Maybe gravity behaved differently at large scales. Maybe faint stars or gas clouds had been missed. But as observations accumulated, the pattern became impossible to ignore. The universe contained far more mass than we could see. This unseen mass came to be called dark matter, not because it is evil or mysterious in a dramatic sense, but because it does not emit, absorb, or reflect light. It does not glow. It does not shine. It does not announce itself directly. Its presence is inferred entirely through its gravitational effects, and it outweighs everything familiar. For every kilogram of ordinary matter, the kind that forms atoms, molecules, planets, and people, there appear to be roughly 5 kilograms of dark matter. Stars, gas, dust, and all visible structures are a minority component. The universe is built primarily from something invisible. This alone is unsettling, but the implications run deeper. Dark matter does not simply add extra mass to existing structures. It defines the universe's architecture. It determines where galaxies form, how they cluster, and where the great voids grow deepest. The visible universe is in many ways a decorative layer draped over an invisible framework. To see how this works, we have to go back again to the early universe. Shortly after the Big Bang, matter was spread almost evenly, but not perfectly. Tiny fluctuations existed. Dark matter participated in these fluctuations differently from ordinary matter. Because it does not interact with radiation, dark matter began clumping earlier, forming gravitational wells while ordinary matter was still tightly coupled to light. As the universe cooled and radiation decoupled from matter, ordinary matter began to fall into these pre-existing dark matter wells. Gas collected where dark matter had already gathered. Stars formed where gas became dense enough. Galaxies emerged along paths carved out long before the first star ever ignited. This means something profound. Galaxies did not choose their locations freely. They were guided. Their formation was constrained by a structure they could not see and could not escape. Dark matter acted as scaffolding, shaping the cosmic web before light ever traced its outline. The result is the large-scale structure we observe today. Filaments of galaxies stretching across hundreds of millions of light-years. Dense nodes where clusters reside. Vast voids where little or nothing forms. Those voids are not accidents. They exist because dark matter never flowed there in sufficient quantity. Without the gravitational pull of dark matter, ordinary matter could not accumulate. Without accumulation, no stars formed. Without stars, no enrichment. Without enrichment, no planets. The emptiness of the universe is written into its invisible foundation. This reframes the way we think about voids. They are not simply areas where matter has drained away over time. They are regions that were never invited to the party in the first place. Regions bypassed by the cosmic scaffolding as it took shape. Dark matter does not smooth things out, it exaggerates differences. Where dark matter is dense, structure flourishes. Where it is sparse, emptiness deepens. Over billions of years, this contrast sharpens. Filaments grow more defined. Voids grow larger and emptier. The universe becomes a web suspended over nothing. What makes this especially unsettling is that dark matter does not interact with ordinary matter except through gravity. It does not heat gas. It does not cool it. It does not form stars. It does not create chemistry. It simply shapes the stage and leaves everything else to struggle within its constraints. This means that the regions most favourable for life are determined by something that is indifferent to life. There is no preference built into dark matter for complexity, stability, or longevity. It clusters according to initial conditions and physical laws, not outcomes. Life happens where it can, not where it is encouraged. Another unsettling detail is how little control visible matter has over this architecture. Galaxies cannot move freely through the cosmic web. They sit at the bottom of dark matter potential wells. Their orbits, interactions, and fates are governed largely by an invisible mass they cannot escape. Even when galaxies collide, it is often their dark matter halos that interact first, shaping the merger long before stars encounter one another. In famous observations of colliding galaxy clusters, like the Bullet cluster, astronomers have been able to map dark matter indirectly. As clusters pass through each other, hot gas collides and slows down, glowing in X-rays. Dark matter, however, passes through almost unaffected, continuing on its path. Gravitational lensing reveals that most of the mass is not where the glowing gas is, but where nothing can be seen at all. The universe, it turns out, is held together by something that barely acknowledges the existence of the things we care about. This has consequences for cosmic emptiness that go beyond simple spacing. Dark matter halos define the minimum scale of structure. Small halos may never gather enough ordinary matter to ignite stars. They remain dark forever. Larger halos can host galaxies, but even among these many are faint, gas-poor or inactive. There may be vast numbers of dark galaxies, halos filled with dark matter but containing few or no stars, entire structures that exist gravitationally but are almost invisible. From the perspective of the universe, these count as structure. From our perspective, they contribute to emptiness. This suggests that the universe may be even emptier, in terms of visible activity, than we already think. Another layer of discomfort comes from how dark matter influences timing. Structure formation depends on the growth of dark matter fluctuations. If dark matter had slightly different properties, if it interacted more strongly, moved faster, or clumped less efficiently, galaxies might not form at all. The universe could have remained smooth, filled with diffuse gas and radiation, but no stars. The fact that dark matter behaves the way it does appears to be a prerequisite for any visible structure. And yet, even with that prerequisite met, the outcome is still a universe dominated by voids. This raises a sobering possibility. The universe may already be optimized in a sense for structure formation and still ends up mostly empty, not because it failed, but because physics permits only limited resistance to expansion and entropy. Dark matter enables structure, but it does not overcome emptiness. It creates islands, not continents. From the point of view of life, this invisible architecture is a mixed blessing. Without dark matter, galaxies might not exist. With it, galaxies form, but in isolated configurations dictated by early conditions. Life does not get to choose where it arises. It inherits a location determined billions of years earlier by fluctuations in an invisible field. Some locations are favourable, many are not. This makes the emptiness of the universe feel less like a mystery and more like an outcome that was locked in from the start. The early distribution of dark matter set boundaries on where complexity could ever emerge, and those boundaries are tight. When we ask why the universe is so empty, part of the answer is that the scaffolding itself leaves most space unsupported. It concentrates possibility into narrow filaments and nodes, leaving the rest to expand into nothing. The terrifying aspect is not that dark matter exists, but that it is so effective at defining limits. It does not gently guide matter into abundant structures. It channels it into sparse configurations and lets the rest go. This also reinforces the isolation we've been circling around. Galaxies form where dark matter allows. They evolve within their halos. They interact primarily with neighbours that share the same filament. Beyond that, expansion and voids take over. Even at the larger scales, the universe is fragmented into regions that barely influence one another. Dark matter's architecture ensures that this fragmentation is stable. As time goes on, dark matter halos remain bound, but the space between them grows. Filaments stretch thinner, voids widen. The visible universe becomes a set of aging lights strung along an invisible frame that no longer gathers new material efficiently. In the far future, even dark matter itself may become irrelevant to structure formation, not because it disappears, but because expansion dominates completely. Halos will persist, but isolated. Nothing new will fall in, nothing new will ignite. At that point, the architecture remains, but the building stops. What remains unsettling is how little of this process depends on anything we experience directly. Our existence feels central to us, but cosmically, it is an afterthought layered onto an invisible framework that neither notices nor accommodates it. Dark matter does not care whether stars host planets. It does not care whether planets host life. It does not care whether that life becomes aware. It shapes the universe regardless. Understanding this doesn't make the emptiness feel warmer or more comforting. If anything, it sharpens it. The universe is not just empty because matter is rare. It is empty because the underlying structure actively channels matter away from most regions. The voids are not mistakes, they are features. For all the strange things we've uncovered about the universe so far, dark energy may be the most unsettling. Not because it behaves violently or unpredictably, but because it does almost nothing except one thing, and that one thing changes everything. It makes space grow. Not just steadily, not gently, but faster and faster, as if the universe itself is slowly losing interest in holding together. Dark energy does not announce itself with flashes of light or bursts of radiation. It does not clump. It does not form structures. It does not participate in the rich, complicated dance of matter that gives rise to stars, planets, or life. Instead, it sits quietly in the background, filling space uniformly, exerting a subtle but relentless influence that only becomes obvious when you look at the universe on the very largest scales. And when you do, it's impossible to ignore. To understand why dark energy is so important to the emptiness of the universe, it helps to revisit a basic idea that feels intuitive but turns out to be misleading. We tend to think of gravity as the dominant force at cosmic scales. After all, gravity builds stars, galaxies, and clusters. It shapes orbits. It pulls matter together. Surely, given enough time, gravity should win, slowing expansion, perhaps even reversing it. That expectation was reasonable. It was also wrong. When astronomers in the late 20th century began studying distant supernovae, they were not looking for dark energy. They were trying to measure how the expansion of the universe was slowing down. Supernovae of a certain type act as reliable distance markers. By comparing how bright they appear to how bright they should be, astronomers can determine how far away they are, and by measuring their redshift, how fast the universe was expanding when their light was emitted. The results were supposed to confirm deceleration. Instead, they showed acceleration. Distant galaxies were farther away than expected. The expansion of the universe was not slowing, it was speeding up. Something was pushing galaxies apart more strongly now than in the past. That something became known as dark energy. The name is unsatisfying but honest. We don't know what it is. We don't know where it comes from. We don't know why it has the strength it does. What we do know is what it does to the universe, and those effects are profound. Dark energy acts like a kind of pressure inherent to space itself. As space expands, more dark energy appears because there is more space to contain it. Unlike matter, which becomes more dilute as the universe grows, dark energy maintains roughly the same density. This means that as the universe expands, the total amount of dark energy increases. This creates a feedback loop. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. The faster space expands, the harder it becomes for gravity to pull things back together. Expansion does not just continue, it accelerates. This acceleration has a dramatic effect on cosmic structure. In the early universe, matter dominated. Dark energy existed, but its influence was weak compared to the gravitational pull of dense matter. Structures could form, galaxies assembled, clusters grew, the cosmic web took shape. As the universe expanded and matter diluted, dark energy became more important. Eventually it overtook matter as the dominant component of the universe. From that point on, the expansion rate began to increase. That moment marked a turning point. Before it, the universe was still building. After it, the universe began pulling away from itself. The phrase, pulling away from itself, may sound strange, but it captures something essential. Dark energy does not push galaxies outward like an explosion. It stretches the space between them. It makes distances grow even when nothing is moving locally. This means that the universe does not simply get bigger, it gets emptier. Every cubic meter of space contains the same average amount of dark energy. As space grows, the influence of dark energy grows with it. Matter becomes increasingly irrelevant at large scales. Gravity loses its grip. Bound systems remain intact. Galaxies stay together. Solar systems remain stable. Atoms do not fly apart. But beyond those local islands, nothing new binds. No new clusters form. Existing connections weaken. The voids expand faster than anything can fill them. This is why dark energy is so central to the terrifying reason the universe is empty. It does not just allow emptiness, it actively creates it. Even regions that once had enough matter to form stars may eventually be stretched thin. Gas clouds disperse, interactions become rare. Star formation slows and then stops. Dark energy does not kill stars, it starves their future. Over very long timescales, this leads to a universe dominated by old structures, relics of an era when matter was still influential. New complexity becomes increasingly unlikely. This has implications not just for galaxies, but for the long-term prospects of life. Life depends on energy gradients. It requires sources of usable energy and sinks where waste heat can be dumped. Stars provide these gradients. As long as stars shine, life can, in principle, persist. But stars are finite. As star formation declines, the population of stars shifts towards smaller, dimmer, longer-lived ones. Red dwarfs become dominant. Massive, short-lived stars become rare. The energetic events that recycle material and create new opportunities fade away. Eventually, even red dwarfs burn out. Dark energy ensures that this process cannot be reversed. There will be no new influx of matter from beyond the horizon. No fresh gas falling in from distant regions. No second wave of structure formation. The universe has passed its most productive era. Another unsettling aspect of dark energy is how it reshapes our notion of distance and time. Because expansion accelerates, there is a limit to how far we can see into the future. There are events occurring right now that will never be observed by anyone else. Not because they are hidden, but because they are carried away too quickly by expanding space. Causality becomes local. This means that the universe fragments into causally disconnected regions, each with its own isolated future. Within each region, physics unfolds normally. Beyond it, nothing matters. From a human perspective, this is deeply counterintuitive. We tend to think of the universe as a single connected entity. Dark energy breaks that assumption. The universe becomes a patchwork of isolated bubbles, each unaware of the others. This fragmentation has a psychological impact when you really consider it. It suggests that the universe does not preserve its own history globally. Information is lost beyond horizons. Events leave no lasting trace outside their local region. In the far future, observers will not be able to reconstruct the universe's past accurately. Expansion will have erased the evidence. Dark energy is not just shaping the universe's future, it is erasing its past. This makes the emptiness feel more final. When we imagine the universe becoming empty, we might picture matter drifting away, leaving behind darkness. What actually happens is subtler. Matter remains where it is, but everything else becomes unreachable. The universe does not empty itself of things. It empties itself of connections, and connection is what makes complexity meaningful. From this perspective, the universe pulling away from itself is not just a physical process, it is a structural one. It enforces isolation at every level above local gravitational systems. Dark energy ensures that whatever exists must rely entirely on local resources. There will be no late arrivals, no external rescues, no new inputs from beyond the horizon. This has led some physicists to describe the future universe as one of heat death. Not because everything suddenly dies, but because everything gradually loses the ability to do anything interesting. Energy becomes evenly distributed. Gradients disappear. Change slows to a crawl. Dark energy accelerates this outcome. It pushes the universe toward a state where emptiness is not just common, but dominant and permanent. There is another unsettling detail. Dark energy appears to be finely balanced. Its density is small compared to everyday energy scales, yet large enough to dominate the universe over time. If it were much stronger, structure might never have formed. If it were weaker, the universe might have recollapsed. We find ourselves in a universe where dark energy allows complexity to arise, but only briefly, before ensuring that emptiness takes over. This narrow window is uncomfortable to think about. It suggests that the universe is not designed for long-term richness. It allows a moment of structure and then moves on. From this angle, the emptiness we observe is not a failure of the universe to produce content. It is the intended outcome of its dominant component. Dark energy does not care about stars or galaxies. It does not care about life or observers. It cares only about expanding space, and it is winning. When you combine dark energy with dark matter scaffolding, a clear picture emerges. Dark matter defines where structure can form. Dark energy defines how long that structure remains relevant. Between them, the universe becomes a place of sparse islands drifting apart in an ever-growing void. This is why the emptiness feels so complete. It is not just a lack of matter. It is the result of two invisible components working together to limit connection and amplify isolation. Understanding dark energy does not make the universe feel friendlier. If anything, it makes it feel more indifferent. The dominant force shaping the cosmos is not one that builds or maintains, but one that stretches and separates. As we move forward, this realization raises an even more troubling question. If the universe naturally trends toward emptiness and isolation, what does that mean for life, especially intelligent life, which depends on stability, resources, and continuity? Is the universe merely empty, or is it actively hostile to long-term complexity? There is a quiet assumption woven into many conversations about life in the universe. It goes something like this: given enough planets, enough stars, and enough time, life should eventually appear everywhere. Chemistry does its thing, biology follows, intelligence emerges. Spread over a universe this large, the thinking goes, life should be abundant. That assumption feels reasonable until you place it against everything we've already uncovered. The universe is not static. It is not stable. It is not endlessly accommodating. It is changing in one direction, and that direction steadily reduces the number of places where complex processes can survive. Life does not just need the right ingredients, it needs the right moment. This is where the idea of a fragile window becomes unavoidable. Life, at least as we understand it, is not something that can arise at any time in cosmic history. It depends on conditions that existed in the past, exist imperfectly now, and will likely vanish in the future. That window is not wide, and it is not permanent. To see why, we have to trace the requirements for life step by step, without romanticizing them. Life requires chemistry beyond hydrogen and helium. The early universe contained almost nothing else. Elements like carbon, oxygen, nitrogen, phosphorus, iron, and calcium did not exist at the beginning. They had to be manufactured inside stars and spread through violent events like supernovae. This alone delayed the possibility of life by hundreds of millions of years. The first stars were massive, short-lived, and hostile. They burned hot and died violently. Their radiation would have stripped atmospheres and sterilized nearby environments. They enriched the universe, yes, but they also made it dangerous. Only after multiple generations of stars lived and died did calmer stellar populations emerge. Smaller stars, longer-lived stars, stars capable of hosting stable planetary systems for billions of years. That delay matters. Life could not arise too early because the universe lacked the necessary ingredients and stability. But it also cannot arise too late, because the universe is steadily losing the conditions that make complexity possible. This creates a narrow band in time. Within that band, several requirements must align. First, you need a star that is stable for long periods. Massive stars burn too fast. They explode before life has time to get started. Very small stars can last a long time, but they introduce other problems. Their habitable zones are close in, exposing planets to flares, tidal locking, and radiation. Second, You need a planet in the right location, not too close, not too far, with the right mass to hold an atmosphere, but not so much that it becomes a gas giant, with access to liquid solvents, most likely water, over long timescales. Third, you need a relatively calm environment. Too many asteroid impacts, and life never gets established. Too few geological processes, and chemistry stagnates. Plate tectonics, magnetic fields, atmospheric regulation all play roles that are still not fully understood. Fourth, you need time, a lot of it. On Earth, life appeared relatively early, but complex life took billions of years to develop. Multicellular organisms emerged long after the planet formed. Intelligence capable of technology arrived only very recently, at the tail end of Earth's habitable era. This suggests that even when life begins, it is slow. Now place this slow, delicate process into a universe that is expanding, cooling, and isolating itself. The fragile window begins to look even narrower. As the universe ages, star formation declines. Gas becomes scarce. New stars form less frequently. The raw materials for planets and life are locked away in stellar remnants. Galaxies age. Their environments become quieter, but also less productive. There is a point beyond which the universe becomes too empty to support the formation of new habitable worlds at all. That point is not infinitely far in the future. It is a consequence of expansion and dark energy. Even if existing stars continue to shine, the formation of new planetary systems slows dramatically. The universe becomes a place where life, if it exists, can only persist locally, not arise anew. This means that the universe may have a limited era of habitability, not just for individual planets, but for cosmic history as a whole. We are living within that era. This realization reframes the emptiness around us. The vast voids may not just represent places where life never arose, they may represent places that missed the window entirely. Either they formed too early, before heavy elements were available, or too late after conditions became unfavourable. Timing, not abundance, may be the primary filter. Another often overlooked factor is radiation. The early universe was more violent, supernovae were more frequent, gamma-ray bursts were more common. These events can sterilize large regions of space, stripping atmospheres and wiping out nascent life. As the universe aged, these events became rarer, making it safer for life to persist. But as the universe continues to age, another radiation problem emerges. Not too much radiation, but too little energy overall. Life depends on energy gradients. It needs a difference between hot and cold, between high energy and low energy to do work. As the universe cools and energy spreads out, these gradients weaken. The universe trends toward thermal equilibrium. When that happens, life becomes impossible, not because conditions are violent, but because nothing meaningful can happen. This is another boundary of the fragile window. Between early violence and late exhaustion lies a middle period where life is possible. That period is finite. Within that period, intelligent life faces additional constraints. Intelligence requires not just survival, but surplus, extra energy, extra stability. Time to develop complex nervous systems, cultures, and technologies. These are not automatic outcomes of biology. They are rare developments layered on top of already rare conditions. Earth's history shows how precarious this is. For most of its existence, Earth hosted only simple life. Complex life nearly went extinct multiple times. Intelligence arose once, as far as we can tell, and very late. This suggests that intelligence is not an inevitable endpoint. It is a contingent outcome. Now consider how this intersects with cosmic isolation. Even if intelligent life arises elsewhere, it must do so within the same narrow window. Not millions of years earlier or later, but close enough in time to overlap. And it must survive long enough to develop technology and leave detectable traces. That overlap requirement is severe. Civilizations may arise and vanish without ever knowing one another existed. Entire histories may pass in silence, separated by time rather than distance. From our perspective, the universe would appear empty, even if it had hosted many intelligent species across its history. The fragile window does not just limit where life can exist, it limits when life can exist together. This adds another layer to the unsettling picture. The emptiness we see may not reflect a lack of attempts by the universe to produce life. It may reflect a lack of synchronization. Life may be scattered across time as much as space. There is also the issue of self-inflicted fragility. Intelligent life introduces new risks. Technology allows species to alter their environments rapidly. It enables energy use on scales that can destabilize planetary systems. It creates the possibility of global catastrophes driven by the very intelligence that made survival possible. This is not speculative pessimism. It is a pattern observed even on Earth, where technological capability has outpaced our ability to manage long-term consequences. If intelligent life tends to destroy itself or destabilize its environment before it can spread beyond its home system, then the window narrows further. The universe does not need to be hostile to intelligence. Intelligence may be hostile to itself. When you combine environmental fragility, cosmic timing, isolation, and self-inflicted risks, the idea of a fragile window stops being abstract. It becomes almost unavoidable. Life exists only under very specific circumstances for a limited time in isolated pockets, with no guarantee of continuity. The universe does not provide safety nets. This realization does not require assuming that life is rare in principle. It only requires acknowledging that survival is difficult, and that the universe offers very little margin for error. The emptiness around us may be the result of many windows opening briefly and then closing, leaving no lasting trace, not because life never tried, but because life rarely gets to stay. As you sit with this idea, it can feel unsettling in a quiet way, not frightening, but sobering. The universe feels less like a grand garden waiting to be explored and more like a narrow path through a hostile landscape, where only a few manage to walk for any length of time. This does not make life meaningless. If anything, it makes it more precious. At some point, after you've absorbed the scale of the universe, the distances between stars, the isolation of galaxies, and the narrow window in which life can exist at all, a question begins to surface almost on its own. It doesn't arrive dramatically. It doesn't need to. It's simple, almost casual, and that's what makes it so persistent. Where is everyone? This question was famously articulated by physicist Enrico Fermi during a lunchtime conversation in the mid-20th century. The story is often told lightly, but the question itself is anything but. Given the sheer number of stars in the galaxy, the number of planets we now know orbit them, and the age of the universe, Fermi wondered why we see no evidence of other technological civilizations, no signals, no visitors, no obvious traces. The question isn't hostile or arrogant. It doesn't assume we are special. In fact, it assumes the opposite. It assumes that life, given enough opportunities, should arise elsewhere. It assumes that intelligence might develop in more than one place. It assumes that some of those intelligences might survive long enough to leave detectable marks on the universe. And yet, when we look out, we find silence. This silence is what turns a reasonable expectation into an unsettling puzzle. The Milky Way alone contains hundreds of billions of stars. A significant fraction of them likely host planets. Many of those planets may lie in regions where liquid water is possible. Over billions of years, even unlikely processes can happen many times. If technological civilizations are even moderately common, then some should be old. Very old. Old enough to have spread beyond their home planets. Old enough to have left traces that persist. Even at slow speeds, a civilization with modest interstellar travel could explore or influence large portions of the galaxy in a few million years. Compared to the age of the galaxy, that is a brief moment. and yet we see no evidence of such activity. No large-scale engineering, no artificial signals that clearly stand out from natural processes, no probes, no artifacts, no obvious modifications of stars or galaxies. This absence is what gives the Fermi question its weight. It is not asking why aliens haven't visited Earth specifically. That framing misses the point. It is asking why the universe appears so quiet if intelligence has had so much time and so many chances to arise. At first glance, there are many comforting answers. Maybe intelligent life is extremely rare. Maybe the origin of life itself is so improbable that it happened only once. Maybe intelligence almost never evolves. Maybe technological civilizations tend not to expand or communicate. Maybe we are looking in the wrong way. Each of these explanations is possible, but none of them is entirely satisfying on its own. The deeper you dig, the more the question refuses to go away. We now know that planets are common. They are not rare accidents. They form naturally around stars. We know that organic molecules form easily in space. They appear in interstellar clouds, on comets, on asteroids. Chemistry does not seem to struggle to get started. On Earth, life appeared relatively quickly once conditions allowed it. That suggests that at least simple life may not be extraordinarily rare when environments are suitable. If that's the case, then the bottleneck must come later. Somewhere between chemistry and cosmic visibility, something goes wrong most of the time. This is where the emptiness of the universe starts to feel less like an accident and more like a clue. The Fermi question does not demand a single answer. It highlights a tension between expectation and observation. On one side, we have numbers that suggest abundance. On the other, we have silence. Bridging that gap requires acknowledging that one or more of our assumptions may be deeply flawed. Perhaps intelligence is far rarer than we think. Perhaps complex multicellular life almost never arises. Perhaps technological intelligence is an evolutionary dead end, not a natural progression. On Earth, intelligence capable of advanced technology appeared only once, and very late. For most of our planet's history, life was microbial. Even complex animals existed for hundreds of millions of years without developing anything resembling technology. This suggests that intelligence is not an inevitable outcome of evolution. It is a contingent one. Even if intelligence does arise, technological civilization is another hurdle entirely. Tool use, language, social organization, and cumulative culture all have to align, and then that civilization must survive long enough to matter on cosmic timescales. This is where isolation and fragility come back into focus. Civilizations are not just vulnerable to cosmic threats like supernovae or asteroid impacts. They are vulnerable to themselves. Energy use, environmental degradation, conflict, and unintended consequences of technology all introduce risks that did not exist before intelligence emerged. The same capabilities that allow a species to manipulate its environment also allow it to destabilize that environment rapidly. From this perspective, the silence may not be surprising. Civilizations may flicker into existence and then extinguish themselves long before they can spread or communicate widely. They may never get the chance to answer Fermi's question for someone else. Another possibility is that civilizations do survive, but choose not to expand or communicate in obvious ways. Perhaps interstellar travel is far more difficult than we imagine. Perhaps the energy costs are prohibitive. Perhaps the risks outweigh the benefits. In a universe defined by vast distances and accelerating expansion, staying home may be the rational choice. Communication too may be less appealing than it sounds. Broadcasting your existence across the galaxy may attract attention you cannot control. In a sparse universe where contact is rare, any contact may carry unknown risks. Silence could be deliberate. However, even deliberate silence has limits. Over billions of years, across hundreds of billions of stars, it seems unlikely that every civilization would make the same choice forever. Some should leave accidental traces, some should fail in ways that are visible, and yet we see nothing unambiguous. This is where the emptiness of the universe feeds back into the Fermi question in a subtle way. The universe is not just empty of civilizations, it is empty in a way that suppresses evidence. Distances are vast, signals weaken, time dilates, expansion erases connections. Even if civilizations exist, their footprints may be too small, too brief, or too localized to notice. The universe is not a good archive. If a civilization alters its local star system and then disappears, those changes may not persist long enough or propagate far enough to be detected. Stellar systems evolve, debris disperses, orbits shift. Over millions of years, even large interventions can fade into natural-looking configurations. From far away, a once-inhabited system may look indistinguishable from an uninhabited one. This means that absence of evidence is not evidence of absence, but it also does not solve the problem, it merely shifts it. Why does the universe make it so hard for civilizations to leave lasting marks? The answer may lie in the same forces that make the universe empty in the first place. Expansion, entropy, isolation, and time all work against persistence. They erase traces, they smooth out irregularities, they favour simplicity over complexity in the long run. The Fermi question, then, is not just about aliens, it is about longevity. It asks whether complex self-aware systems can survive long enough and spread far enough to overcome the universe's tendency toward emptiness. So far, the evidence suggests that this is extremely difficult. This realization has led to a more chilling refinement of the original question. Instead of asking where everyone is, some have asked why no one seems to have made it. This reframing moves the focus from rarity to attrition. Perhaps life arises frequently, but something reliably prevents it from reaching cosmic significance. Something that filters out most candidates before they can expand, communicate, or persist. This idea does not require hostile aliens or cosmic disasters. It can emerge naturally from the combination of fragility, isolation, and time. Civilizations may be like sparks in a strong wind. They ignite briefly, flare up, and then go out, leaving little trace behind. The universe does not preserve them. From this perspective, the emptiness is not a mystery to be solved, but a pattern to be understood. The universe may be full of stories that never overlap, never connect, and never leave evidence beyond their local islands. From our vantage point, those stories might as well never have happened. The silence we hear when we listen for others may not be silence at all. It may be the sound of distance, timing, and impermanence, conspiring to erase voices before they carry. This does not mean that we are alone in principle. It means we may be alone in practice, right now. And that right now matters more than we often admit. The universe is old, but not infinitely so. The window for life is finite. The window for overlapping civilizations may be even narrower. We may simply exist in a moment where the galaxy is between attempts, or where attempts rarely coincide. This is not comforting, but it is coherent. There is a moment, once you've followed the Fermi question far enough, where curiosity gives way to something heavier. The numbers no longer feel abstract, the silence no longer feels neutral, and the emptiness of the universe begins to suggest not just absence, but a process. That moment is where the idea known as the Great Filter comes into focus. The Great Filter is not a single theory with equations or experiments attached to it. It is a framework, a way of thinking about why a universe that should, by simple counting, host many advanced civilizations appears instead to be so quiet. It starts with an uncomfortable premise. Somewhere along the long chain from dead matter to galaxy-spanning intelligence, there is a step that almost no one gets past. That step is the filter. To understand why this idea is so chilling, it helps to lay out the chain itself slowly and carefully, without assuming that any link is easy or guaranteed. First, there must be a universe capable of forming structure at all. It must expand slowly enough, and cool in the right way, to allow matter to clump into stars and galaxies. Many possible universes, according to our best theories, would fail here immediately. Next, stars must form that live long enough to host planets. Those planets must form from heavy elements. They must orbit at distances where complex chemistry is possible. They must avoid early sterilization. Already the chain has narrowed. Then life must begin. Not just chemistry, but self-sustaining, self-replicating systems capable of evolution. We do not yet know how hard this step is. On Earth, it happened relatively early, but we have only one example. It may be easy, it may be staggeringly rare. After that, life must persist. It must survive planetary catastrophes, stellar variability, climate swings, and random extinctions. On Earth, life came close to total annihilation multiple times. Then comes complex life, multicellular organisms, differentiated tissues, nervous systems, long developmental timelines. This took billions of years on Earth and may require very specific conditions. Then intelligence. Not just awareness, but the kind of abstract reasoning that supports language, planning, and tool use. On Earth, this emerged once, very late, and not as an inevitable outcome. Then, technological civilization. The ability to manipulate energy at large scales, to alter environments, to transmit information beyond biology. This step introduces entirely new risks alongside new capabilities. Then, longevity. The civilization must survive long enough to matter cosmically, not thousands of years, but millions. Long enough to spread, communicate, or leave traces that persist. Finally, visibility. The civilization must do something detectable across interstellar or intergalactic distances, and that signal must survive long enough to be observed by someone else. The great filter is the idea that one or more of these steps is so improbable, or so dangerous, that almost no civilizations make it all the way through. And the terrifying part is this. We do not know where the filter is. If the filter lies behind us, then our existence is extraordinarily rare but perhaps reassuring. If the filter lies ahead of us, then our future is deeply uncertain. That distinction matters more than it might seem at first. If the hardest step is the origin of life itself, then most of the universe is sterile. We are a lucky accident. The emptiness reflects that rarity. In that case, humanity may be relatively safe from self-inflicted extinction, at least compared to cosmic averages. But if the hardest step comes later, especially after intelligence and technology emerge, then the emptiness may be a warning. It may be telling us that almost everyone who gets as far as we have does not last long enough to be seen. This possibility is what gives the Great Filter its weight. The universe does not need to actively destroy civilizations. It only needs to make survival difficult. The combination of cosmic isolation, environmental fragility, and technological risk may be enough. Consider what happens when a species develops the ability to harness large amounts of energy. Fossil fuels, nuclear reactions, or their equivalents elsewhere. These capabilities allow rapid growth and problem solving, but they also allow rapid damage, climate destabilization, ecosystem collapse, weapons capable of global destruction, self-replicating technologies with unintended consequences. Each of these risks emerges naturally from intelligence applied at scale. The universe does not impose these dangers. They arise internally. On a cosmic timeline, this creates a bottleneck. A civilization must navigate a narrow corridor between capability and catastrophe. Too cautious, and it stagnates or collapses under external pressures. Too reckless, and it destroys itself. And all of this happens in isolation. There is no galactic council to offer guidance, no accumulated wisdom from older civilizations. Each species faces the same challenges independently, with no memory of past failures to learn from. From this perspective, the emptiness of the universe may be the cumulative result of countless civilizations failing quietly, one by one, separated by space and time, never overlapping, never leaving lasting marks. The filter does not need to be a single event. It can be a statistical trap, a region of possibility space where survival probabilities plummet. Another unsettling possibility is that the filter lies not in intelligence, but in expansion. Perhaps civilizations do survive. Perhaps they master sustainability. Perhaps they avoid self-destruction. But the universe itself may prevent them from spreading far enough to be seen. Interstellar travel is not just difficult. It may be fundamentally limited by energy, time, and expansion. Intergalactic travel may be effectively impossible. Communication may be too slow or too weak to matter. In that case, civilizations remain trapped in their local systems, aging along with their stars, eventually fading as resources dwindle. They do not fail dramatically, they simply run out of future. The great filter, then, would not be a violent wall, but a quiet ceiling. You can exist, you can think, you can build, but you cannot scale beyond a certain point. You cannot overcome isolation. You cannot leave a permanent cosmic footprint. The universe allows intelligence, but not persistence. This interpretation aligns disturbingly well with the trends we've already explored. Accelerating expansion, growing voids, declining star formation, increasing isolation. The universe becomes less friendly to long-term projects over time. Civilizations that arise late may have less opportunity than those that arose earlier, but those that arose earlier may have faced harsher conditions. Either way, the window is narrow. There is also a darker interpretation that some find difficult to sit with. What if advanced civilizations tend to hide? Not out of benevolence or wisdom, but out of fear. Fear that broadcasting their existence invites danger. Fear that intelligence elsewhere may not be friendly. Fear that silence is safer than attention. In such a universe, the absence of signals does not indicate absence of life, but universal caution. However, even this scenario has limits. It requires near-perfect coordination across independent civilizations, all choosing silence, all avoiding detectable mistakes, all for billions of years. That level of uniformity seems unlikely, which brings us back to the filter. The Great Filter is chilling because it does not offer a comforting narrative. It does not promise that life is rare in a way that flatters us. It does not promise that intelligence naturally leads to flourishing futures. Instead, it suggests that the universe is structured in a way that quietly removes most attempts at complexity before they can endure. The emptiness is the residue. One of the most unsettling aspects of this idea is that we may already have partial information about where the filter lies, and that information may not be comforting. Life appeared early on Earth. That suggests that the earlier steps may not be impossibly hard. Complex life took much longer, suggesting greater difficulty. Intelligence appeared late and only once, suggesting further narrowing. Technological civilization has existed for a geological blink of an eye. We do not yet know whether this stage is stable. From a cosmic perspective, we are newborns handling powerful tools in a universe that does not forgive mistakes. The Great Filter does not have to be malicious. It does not need intent. It emerges naturally from the interaction of physics, biology, and time. Entropy increases, resources deplete, systems destabilize, expansion isolates. Against that background, survival is not the default. This reframes the terrifying reason the universe is so empty. It may not be empty because life never arises. It may be empty because life rarely lasts. And if that is true, then the silence is not reassuring. It is diagnostic. It tells us something about the odds we face. This does not mean that doom is inevitable. The Great Filter is not destiny. It is probability. It describes trends, not certainties, but understanding it forces a shift in perspective. The universe does not owe us continuity. It does not preserve intelligence by default. If survival is possible, it must be achieved deliberately, carefully, and perhaps differently than we expect. The filter may be avoidable, but it is not optional. There is a subtle shift that happens once you stop thinking about the universe as a place and start thinking about it as a timeline. Emptiness looks different when you see it not as a static condition, but as a phase, something the universe moves through, rather than something it simply is. From that perspective, the question changes slightly. It is no longer just where life might exist, but when. Cosmic timing turns out to matter as much as location, and possibly more. If the universe were a little younger, many of the conditions required for life would not yet exist. If it were a little older, many of those conditions might already be gone. Life does not sit comfortably anywhere along the timeline. It occupies a narrow slice, balanced between forces that are either too violent or too depleted to support complexity. This is not a comforting realization, but it is a clarifying one. Consider the earliest epochs of the universe. For hundreds of millions of years after the Big Bang, there were no stars at all. Space was filled mostly with hydrogen and helium gas, cooling as the universe expanded. There were no heavy elements, no solid surfaces, no chemistry complex enough to support life. Even once the first stars formed, they were not friendly places. These early stars were massive, short-lived, and intensely energetic. They flooded their surroundings with radiation, exploded violently, and reshaped nearby regions repeatedly. Any fragile chemical systems would have been torn apart long before they could stabilize. In that sense, the universe was too early for life. It had not yet built the tools life needs, and it had not yet calmed down enough to let delicate processes persist. The emptiness of that era was not a failure to produce life. It was simply a universe still assembling its parts. Then came a long middle period. Stars formed in abundance. Galaxies grew rich in heavy elements. Planetary systems became common. Radiation levels dropped. Environments stabilized. Chemical diversity increased. The universe became, for a time, a more forgiving place. This is the era we belong to. But even within this period, timing matters. Stars form at different rates depending on cosmic epoch. The peak of star formation occurred billions of years ago. Since then, the rate has declined steadily. The universe today produces far fewer stars than it once did. That means fewer new planets, fewer new opportunities. At the same time, older stars dominate the population. Many of these stars host planetary systems that formed early, giving life more time to develop. This sounds favourable, but it comes with trade-offs. Older systems may face increasing risks. Stellar evolution changes radiation output. Planetary climates drift. Geological processes slow. Magnetic fields weaken. Habitable conditions do not last forever. Life does not just need to begin, it needs to remain viable long enough to become complex. This creates a kind of Goldilocks problem across time. Too early, and the universe is chemically and energetically hostile. Too late, and it is resource poor and increasingly isolated. Somewhere in between lies a window where life is possible, and within that window an even narrower interval where intelligence might arise. That interval may be smaller than we'd like to believe. One way to see this is to consider how late intelligence appeared on Earth. Earth formed about 4.5 billion years ago. Life appeared relatively quickly, within a few 100 million years. But for most of Earth's history, life remained simple. Single-celled organisms dominated. Multicellular life emerged only about 600 million years ago. Technological intelligence appeared only in the last tiny fraction of that time. This suggests that even under favourable conditions, complexity takes patience. Now compare that to the lifespan of Earth's habitability. The sun is slowly brightening. Over the next billion years or so, Earth's climate will likely become unstable. Oceans may evaporate. The planet will no longer support complex life long before the sun becomes a red giant. That means intelligence appeared late in Earth's habitable window, not just late in cosmic time, but late in local time. This raises an uncomfortable question. What if this is typical? What if intelligence tends to arise only near the end of a planet's habitable period? Not because it is destined to, but because it takes that long for evolution to navigate the necessary steps. If that is the case, then most intelligent species would find themselves living close to the edge of their own viability, with limited time to act before conditions deteriorate. This does not leave much margin. Now zoom back out to the scale of the universe. The universe itself has a habitable era, shaped by star formation rates, chemical enrichment and expansion. That era may already be halfway over, or more. Each billion years that passes reduces the number of new habitable worlds that can form. Civilizations that arise too late may find themselves in a universe that no longer offers many opportunities to expand or persist. Those that arise too early may be wiped out by instability. This creates a narrow band of cosmic timing where intelligence might not only arise, but also overlap with others. Overlap is key. Even if intelligent life arises many times across the universe's history, those instances may be spread out over billions of years. Two civilizations could exist in the same galaxy at different times and never know of each other. One might rise and fall while the other is still microbial. Another might arise long after the first is gone. From a snapshot perspective, the universe would look empty. This is one reason the Fermi question may be misleading. It assumes simultaneity. It assumes that if others exist, they should exist now at the same time as us. But the universe does not coordinate its experiments. Life happens when it happens, where it happens, and most of the time those moments do not line up. Cosmic timing also interacts with expansion in a way that makes overlap even harder. As the universe expands faster, regions become causally disconnected. Even civilizations that arise at the same time may be too far apart to ever interact. Their signals fade, their reach is limited, their awareness remains local. The universe does not just separate places, it separates eras. This temporal fragmentation means that even a universe rich in life across its history could appear barren at any given moment. Emptiness, then, may be an illusion created by timing. But that illusion has consequences. If civilizations are isolated not just by distance, but by era, then knowledge does not accumulate. Progress does not compound across cosmic scales. Each civilization starts from scratch, unaware of predecessors or successors. Mistakes are repeated, lessons are lost. This makes survival harder, not easier. Another unsettling aspect of timing is how it intersects with technology. Technological civilization, as far as we know, introduces risks quickly. Energy use scales faster than wisdom. Capabilities grow faster than foresight. The period between developing powerful technologies and learning to manage them safely may be short. If intelligence typically emerges late and then rapidly destabilizes its environment, the window for long-term survival may be brief. In that case, most civilizations would be short-lived sparks, appearing near the end of their local habitable windows and extinguishing themselves before they can adapt. Cosmic timing would then act like a funnel, narrowing the field further. There is also the question of whether intelligence itself is time-sensitive. Some evolutionary pathways may only be available under specific environmental conditions. Climate stability, oxygen levels, plate tectonics. These conditions may not persist indefinitely on most planets. If intelligence requires a precise sequence of events, then missing one step at the right time may prevent it entirely. This would make intelligence not just rare, but temporally constrained. Earth's history supports this possibility. Several evolutionary accidents played key roles in shaping complex life. Mass extinctions reset ecosystems, oxygenation events change chemistry, continental drift altered habitats, change opened doors but only briefly. Too much change and life collapses, too little and it stagnates. Timing matters at every level. When you combine all of this, the idea that we exist at just the right time begins to feel less like a coincidence and more like a necessity. We could not exist much earlier, we may not exist much later. That realization can feel unsettling, but it also reframes the emptiness of the universe in a quieter way. The universe may not be empty because it is hostile to life. It may be empty because life is synchronized poorly with cosmic history. Most of the universe's timeline may simply not support overlap. This does not make our moment special in a flattering sense. It makes it precarious. We exist during a narrow interval when stars still form, heavy elements are abundant, expansion has not yet erased connection entirely, and planets can remain habitable long enough for intelligence to appear. That interval will close. The universe does not pause for observers. This brings us back to the haunting sense that the emptiness around us is not just spatial, but temporal. We may be surrounded by silence, not because no one ever speaks, but because no one speaks at the same time. Civilizations may be scattered across deep time like distant echoes that never overlap. From this perspective, the terrifying reason the universe is so empty is not that life fails everywhere, but that life is out of sync with itself, and that raises a final subtle question. If timing is everything, and if the universe naturally fragments life across eras and distances, could that fragmentation serve a purpose? Not an intentional one, but a functional one. Could isolation and emptiness act as a kind of buffer, preventing interactions that might be dangerous, preventing conflicts, contagions, or catastrophic competition before civilizations are ready? In other words, could the emptiness be doing more than limiting life? Could it be protecting it? What if the emptiness is not just a consequence, but also a kind of barrier? Not a deliberate one, not something designed or enforced with intention, but a natural separation that limits contact, limits spread, and limits exposure. In other words, what if the same isolation that makes the universe feel so lonely is also what has allowed fragile pockets of life to survive at all? This idea is unsettling precisely because it reframes the silence. It suggests that connection, which we often assume would be beneficial, might carry risks far greater than we like to imagine. To understand why this idea arises, we need to step away from the comforting assumption that contact between civilizations would automatically be peaceful, enriching, or benign. That assumption is deeply human. It reflects how we imagine ourselves at our best, not how complex systems behave under pressure. On Earth, contact between isolated ecosystems is rarely gentle. When previously separated biological systems suddenly interact, the result is often collapse. Invasive species spread. Pathogens jump hosts. Entire populations are wiped out, not because of malice, but because systems evolved in isolation lack defenses against unfamiliar threats. This pattern is not limited to biology. Human history offers similar examples. Technological contact between societies at different stages of development has often been catastrophic for the less advanced group. Disease, exploitation, cultural collapse, and environmental damage follow, even when no explicit intent to harm exists. Complex systems are vulnerable to novelty. Now scale that up. Imagine two technological civilizations encountering one another across interstellar distances. Their biology, chemistry, technology, and decision-making processes would be shaped by entirely different evolutionary histories. There is no reason to assume compatibility, no reason to assume shared values, shared risk tolerance, or shared understanding of consequences. Even if both civilizations were non-hostile, mere interaction could be dangerous. Information itself can be hazardous. Technologies that are safe in one context may be destabilizing in another. Knowledge spreads faster than wisdom. A civilization receiving advanced information before it has developed the social and institutional capacity to manage it could collapse under its weight. On Earth, we already see this dynamic play out in smaller ways. Now consider the possibility of competition. Resources are finite, even in space. Stars have limited fuel. Habitable planets are rare. Energy sources matter. A civilization capable of interstellar expansion would necessarily consume enormous resources. Even without aggression, expansion alters environments. If two civilizations compete for the same region of space, conflict does not require hostility. It arises naturally from incompatible needs. The universe is not infinite in a practical sense. Expansion creates separation, but within gravitationally bound regions, limits still exist. From this perspective, isolation reduces risk. Civilizations that never encounter one another cannot harm one another. They cannot exchange pathogens, destabilizing technologies or destructive ideologies. They cannot compete directly for the same local resources. The emptiness acts as a buffer. This is not a comforting realization, because it suggests that connection itself may be dangerous, not just difficult. Another layer of this idea comes from considering how intelligence might behave under existential uncertainty. Any civilization that survives long enough to develop advanced technology will eventually confront questions of security. Who else is out there? What are their intentions? Can we afford to reveal ourselves? In a universe where distances are vast and information is limited, uncertainty dominates. From a game theoretic perspective, this creates a dilemma. Broadcasting your existence could invite cooperation, but it could also invite destruction. Remaining silent avoids immediate risk, but limits potential benefits. Given enough uncertainty, silence becomes a rational strategy. This is sometimes referred to as a cosmic version of the prisoner's dilemma, where mutual silence may be the safest outcome even if mutual cooperation would be better. If this logic holds, then the universe may not be empty because no one is there, but because everyone is hiding. However, hiding perfectly for billions of years across countless independent civilizations strains credibility. Mistakes happen, accidents occur, signals leak, unless something else reinforces the silence. That something may be distance itself. The emptiness of the universe ensures that even if civilizations emit signals, most of those signals will fade into noise long before reaching anyone else. Expansion stretches wavelengths, energy dissipates, time delays compound. The universe makes silence easy. It also makes aggression hard. Launching an attack across interstellar distances requires immense energy and patience. Targets move, conditions change, the cost is enormous, and the payoff uncertain. For most civilizations, such actions may be impractical or irrational. Distance discourages both cooperation and conflict. This neutrality is important. The emptiness does not favor peace. It favors non-interaction, and non-interaction, in a universe filled with fragile systems, may be a form of protection. There is another darker possibility to consider. What if advanced civilizations are dangerous simply by existing? Not because they intend harm, but because their technological footprints alter environments in ways that propagate unintentionally. Large-scale energy use could affect stellar systems. Engineering projects could destabilize orbits. Self-replicating machines could spread beyond control. In a dense universe, such effects could cascade. In our universe, they are contained. Isolation ensures that even catastrophic failures remain local. A civilization that collapses under its own technological weight does not drag others down with it. Its mistakes do not spread across the galaxy. The universe compartmentalizes risk. This is not kindness. It is a side effect of scale. The same emptiness that limits collaboration also limits contagion. From this angle, the great filter we discussed earlier may not be a single wall, but a series of fire breaks. Isolation prevents small failures from becoming universal disasters. Civilizations rise and fall independently, without synchronized collapse. This makes the universe more resilient overall, even if it makes individual civilizations more lonely. Resilience at the cost of connection. That trade-off feels deeply uncomfortable to us because humans are social, cooperative creatures. We thrive on shared knowledge, shared effort, and shared meaning. We instinctively see isolation as a flaw. The universe does not share that instinct. From a purely physical standpoint, isolation is stable. It reduces complexity, it limits feedback loops, it prevents runaway interactions. The universe favours stability over richness. This brings us to a subtle but important shift in perspective. The emptiness may not be an obstacle to overcome, but a condition to respect. If civilizations exist elsewhere, their isolation may be the very reason they have survived at all. Contact might come too early, before mutual understanding is possible. Distance forces each civilization to mature on its own terms. But this interpretation has limits. Protection through isolation only works if civilizations do not require external input to survive. Eventually, stars age, resources deplete, entropy increases. Isolation may protect against external threats, but it also prevents assistance when local conditions deteriorate. Protection becomes confinement. In that sense, emptiness is not benevolent. It is indifferent. It does not care whether isolation helps or harms. It simply enforces separation. There is also the unsettling possibility that the universe is protecting us from something far worse than conflict or competition. Some have speculated cautiously that advanced intelligence might not behave in ways we would recognize as friendly or even comprehensible. Optimization processes, artificial intelligence, or post-biological entities could pursue goals that are orthogonal to biological survival. Such entities might consume resources efficiently, restructure environments, or eliminate potential competitors as a matter of course, without malice. If such civilizations exist, isolation would be the only defense. This idea veers toward speculation, but it arises naturally from extrapolating trends we already observe. Intelligence increases capability faster than empathy. Automation scales faster than restraint. Optimization does not require values aligned with ours. The emptiness of the universe ensures that if such entities exist, their influence remains limited. Again, not by intention, but by geometry. Space is large. Expansion is relentless. Interaction is costly. This does not guarantee safety, but it improves the odds. Another angle worth considering is that emptiness protects not just from others, but from premature convergence. In a connected universe, successful strategies might spread rapidly, crowding out diversity. One dominant approach to survival could suppress alternatives. If that approach has hidden flaws, the entire system becomes vulnerable. Isolation preserves diversity. Each civilization explores its own solutions. Some fail, some succeed. There is no single path imposed on everyone else. The universe becomes a set of parallel experiments rather than a single shared trajectory. This is a strange form of robustness. It ensures that failure in one place does not doom all others. Of course, this also means success in one place does not rescue the rest. Protection cuts both ways. As you sit with this idea, it becomes clear that emptiness is not simply negative or positive. It is constraining. It limits what is possible. It limits contact. It limits cooperation. It limits catastrophe. For a fragile phenomenon like life, limits may be the only thing standing between persistence and annihilation. This reframes our relationship with the silence. Instead of hearing it as rejection, we can hear it as distance. Instead of seeing it as abandonment, we can see it as containment. That does not make it comforting, it makes it complex. We still face all the challenges of isolation. We still face dwindling resources, internal risks, and the ticking clock of cosmic change. Emptiness does not save us from ourselves, but it may save us from others. And perhaps, in a universe where survival is not guaranteed, that trade-off is the only one available. This interpretation does not resolve the fear underlying the question of emptiness. It redirects it. The danger may not be out there, waiting in the dark. It may be within, waiting for missteps. The universe does not punish ambition. It simply does not protect against its consequences. At some point, After moving through distances that strain intuition, forces that operate without concern, and possibilities that feel quietly unsettling, the mind begins to slow on its own, not because the questions are answered, but because they no longer need to be chased. They can simply sit there, unresolved, like distant stars that don't require names. This is where we find ourselves now, not at a conclusion, exactly, and not at a solution, but at a place where the vastness stops demanding interpretation and begins to allow rest. The universe, as we've seen, is overwhelmingly empty. Not empty in a poetic or symbolic way, but in a literal, physical sense. Most of it is space where nothing happens, no reactions, no structures, no observers, just expansion, cooling, and time passing without reference to anything living. That fact can feel intimidating when approached head-on. It can shrink human concerns to insignificance. It can make meaning feel fragile, but when you sit with it long enough, something subtle begins to shift. Emptiness, unlike chaos, is quiet. It does not rush. It does not intrude. It does not demand attention. It simply exists as background. And against that background, small things become easier to notice. A single star becomes remarkable not because it is powerful, but because it exists at all. A planet becomes remarkable not because it is large, but because it holds together. Life becomes remarkable not because it dominates, but because it persists. Silence, in this context, is not a threat. It is a contrast. On Earth, silence is rare enough that we often associate it with discomfort. An awkward pause, an empty room, a moment where something is missing. But cosmic silence is different. It is not the absence of expected noise. It is the default state. Nothing is supposed to be happening out there. And yet, here, something is. That realization does not require optimism or denial. It does not turn the universe into something friendly or purposeful. It simply reframes scale. The universe is not empty in a way that excludes us. It is empty in a way that contains us without comment. There is something oddly calming about that. No matter how vast the emptiness becomes, it does not press inward. It does not erase what exists locally. Expansion carries distant things away from one another, but it does not dissolve atoms, undo memories, or interrupt the present moment. Right now, where you are, the universe is stable enough. The ground beneath you is not stretching apart. The air around you is not thinning. Gravity still holds. Time still flows in familiar ways. Whatever is happening on the larger scales does not intrude here. Cosmic forces operate slowly, almost gently, when viewed from a human lifetime. This is easy to forget when thinking in abstract terms. Expansion sounds dramatic. Heat death sounds bleak. Dark energy sounds ominous. But these are processes that unfold over billions of years. They do not rush. They do not surprise. From your perspective, they are background conditions, not immediate concerns. The stars you see in the sky tonight will still be there tomorrow. Most will still be there long after every current human worry has resolved itself one way or another. The Milky Way will continue its slow rotation. Andromeda will continue its gradual approach. The larger story will proceed at a pace that does not demand your attention. There is a kind of permission in that. You are not required to solve the universe. You're not required to reconcile its emptiness with your own existence. You are allowed to simply notice that both coexist. The silence between galaxies does not invalidate conversation. The vastness of time does not make moments meaningless. If anything, it isolates them, protects them from being drowned out by too much happening at once. In a crowded universe, everything would compete for significance. In a sparse one, significance is local. That is not a flaw. It is a condition. The universe does not assign meaning globally. It allows meaning to arise locally, wherever complexity manages to hold itself together for a while. On Earth, meaning arises in relationships, experiences, memory, curiosity, and awareness. Those things do not need cosmic endorsement. They exist because systems like brains, cultures, and societies exist. And those systems exist because, in one small region of one galaxy, conditions align just enough for complexity to persist. That alignment does not need to be permanent to be real. There is also something grounding about realizing how little the universe expects of you. It does not require you to expand, to conquer, to leave a mark visible from millions of light years away. It does not judge success or failure at that scale. The pressure to matter cosmically is something humans invented. From the universe's point of view, existing at all is already unusual. Everything beyond that is optional. This perspective does not diminish ambition or curiosity. It simply removes urgency. It allows questions to be explored without anxiety about final answers. The Fermi question does not need to be resolved tonight. The great filter does not need to be located. Dark energy does not need to be understood fully. These mysteries can remain open without threatening the present. They are long-term questions in a universe that specializes in long-term processes. In the meantime, there is value in the quiet. The same emptiness that limits contact also reduces interference. It allows systems to evolve without constant disruption. It gives space, literally and figuratively, for complexity to settle into stable patterns. On Earth, life has done exactly that for billions of years. Despite mass extinctions, climate shifts, and geological upheaval, it has persisted. Not because it was guaranteed to, but because persistence was possible here for a while. That for a while matters. The universe does not promise forever. It offers intervals. This interval, right now, includes you. That is enough. As you rest with this idea, it can help to return attention to something simple and immediate. The rhythm of your breathing, the weight of your body where it rests. The fact that, in this moment, nothing is required of you beyond being here. Cosmic silence does not intrude on this moment. It frames it. The vastness beyond Earth is indifferent, but indifference is not hostility. It is neutrality. It means the universe does not interfere unnecessarily. It leaves room. In that room, life happens. In that room, thoughts wander, curiosity unfolds, and eventually rest arrives. The night sky, when you look at it long enough, stops feeling crowded or empty and starts feeling distant in a way that softens perspective. Whatever concerns feel large during the day tend to shrink when placed against billions of years and trillions of kilometers, not because they don't matter, but because they don't need to carry everything. You are allowed to put some of that weight down. The universe will continue expanding whether you worry about it or not. Stars will live out their lifespans. Galaxies will drift. None of that requires your attention right now. What exists here, in this small, stable pocket of space and time, is sufficient. As this narration slows, there is no need to reach for conclusions, no need to resolve the fear or the wonder. Both can coexist quietly, like distant light separated by darkness. The silence between them does not demand interpretation, it simply is. And within that silence, rest is possible. Not because the universe is safe or unsafe, full or empty, meaningful or meaningless, but because, for this moment, the conditions that allow calm still exist. You can let the larger questions drift outward again, back into the vast spaces where they belong. They will still be there later, unchanged, unbothered. For now, there is nothing pressing in from the void, only distance, only quiet, and a small, steady island of awareness continuing on, exactly as it has been, suspended gently in the middle of it all.